Chaque zone de l'UM6P est équipée d'un plan d'évacuation qui indique les sorties de secours et les gestes à tenir en cas d'urgence. Prenez votre temps de l'observer ou demandez de l'accompagnement par le staff organisateur de l'événement. En cas d'écoute d'alarme, prendre du temps, ne pas se précipiter, suivre les équipiers d'évacuation ou le chemin le plus proche vers une sortie de secours indiquée par cette signalétique. Ne pas utiliser l'ascenseur. Une fois dehors, se déplacer vers le point de rassemblement pour confirmer votre sécurité au responsable d'évacuation et ne pas quitter le point de rassemblement qu'après autorisation. Si vous êtes le premier à notifier une situation d'urgence au sein des lieux de l'événement, vous devez activer le système d'alarme en poussant sur les déclencheurs manuels. Nos équipes sont à votre disposition et vous souhaitent un excellent événement.
Ladies and gentlemen, dear guests, dear students, good morning. Well, the French have a saying, les meilleures choses ont une fin, which could translate roughly as even the best things come eventually to an end. So, this is the fifth and last day of this year's UM6P Science Week. Last day, not the least, actually, the program this morning is richer than a Yorkshire pudding. It's really rich. Today, your Master of Ceremony will be my friend and colleague, Sarah Alami, who is Research Education Fellow at the School of Collective Intelligence. As I said during the first session of the first day, the School of Collective Intelligence of UM6P is the only place in the whole world, and possibly in the whole galaxy, where you can actually get a master degree in collective intelligence. It was founded by my friend and colleague Lex Paulson, another friend. I am blessed in having not only a lot of friends, but very, very clever friends. This morning we'll have 5 talks. Geoffrey WEST, by the ebullient Virginia CHAITIN, by Mr. Cool himself, David Napier, James Winter, Katherine PEIL. Stuart KAUFFMAN is also going to discuss Geoffrey West's talk. As I said, it's a very, very rich session this morning. We have to stay concentrated for at least 4 hours. Without further ado, I will ask Sarah Alami to join me and to tell us more about the program concocted this morning by the School of Collective Intelligence. Sarah.
Good morning, everyone, and welcome to our session entitled Complex Problems and Collective Solutions. So I'm Sarah Alami, a Research and Education Fellow at the School of Collective Intelligence, and it's my honor to moderate this session. Our school is a multidisciplinary department that brings together the cognitive, political, anthropological, and computational sciences with the aim of leveraging collective intelligence to understand fundamental scientific questions and solve complex problems. So collective intelligence refers to the emergent ability of groups to devise solutions to challenges which none of their members could overcome on his own or individually. And so our session today focuses on exactly that. So the complex problem that we face right now on our planet and the ways in which we might collectively overcome them. And so we are going to begin with a plenary talk from our very special guest, Dr. Geoffrey WEST, who is joining us from Santa Fe, New Mexico, and who has very kindly agreed to give this talk despite the large time difference. So Dr. Geoffrey WEST is a distinguished professor and former president of the Santa Fe Institute. He's a theoretical physicist with a diversity of research interests, from metabolism, cancer and aging, to the study of growth, innovation, and the life history of cities. He's also the author of the best-selling book Scale, and he has his work featured by outlets like the New York Times, National Geographic, The Economist, BBC, and others. So without further ado, I'll pass the floor to Dr. Geoffrey WEST.
Thank you, Sarah. Thanks for that introduction, and thank you for the organizers and yourself for inviting me. Absolutely delighted to be involved in this. I'm just extremely disappointed that I can't be there in person. This is, not a very satisfactory way of delivering a talk, but let's see how it goes. I hate this kind of two-dimensional, soulless way of doing it. I don't know if it's up on the screen, but that's the title in the program of my talk. And indeed, I am going to talk about pretty much all of these things to varying degrees. I won't talk about companies, entreprise, but I will talk about the various other things. But here's an alternative title in English, which is also what I'm going to be talking about, because I'm quite passionate about thinking about the future of the planet and the multiple dynamics that is going to control what the future will be like. And I want to talk about that. And the talk covers, look at the title is, sort of allows me to talk about almost anything, but it's going to be very broad. A lot of the work is actually quite technical, mathematical. I won't touch on that. I'll keep it at a very big picture level, sort of 100,000 meter view of things, and sort of impressionistic. But I want to get ideas across and concepts across, and I'm going to do it by first focusing on the planet itself, and then I'm going to deconstruct and then come back to it. So when you think of when you have the word planet, and our globe, this is sort of the image that you conjure up. But of course, that's very misleading, because this is much more what the Earth really looks like these days. It's dominated by cities, dominated, of course, by the presence of human beings. And because of that, the word Anthropocene has been conjectured as a way of describing this. That is the dominance of the effect of man, woman on the planet. But in fact, what I'm also going to be talking about is a result of that, and something that I think hasn't received enough attention, is the dominance of the planet by cities. And I like the word urbanocene to connote that. And just to give a sense of what that is, I have fantasized as to what a photograph taken by a NASA satellite would have looked like in the year 1840. And as you can see, you can barely see anything. But in 100 years later, 1940, you can see something. I chose this year, by the way, because it's the year I was born. And this is my estimate of what it would look like roughly in 1940. And of course, all those lights are the lights of cities. And they represent the extraordinary urbanization that has taken place on the planet. That now looks like this. That's a relatively recent photograph of the Earth taken by a NASA satellite. And of course, that is the glow of the cities. And you can see the rapid increase of urbanization that's taken place in what is a relatively short period of time. And even though that represents the glow of the cities, what it really represents is the Earth burning up. That's the Earth burning, because all of those lights are fueled by fossil fuels, and it is literally the surface of the Earth burning. And only someone foolhardy and thoughtless would not believe that this has a profound effect upon the climate of the planet and the atmosphere of the planet. So just put some of this urbanization into numbers to begin with. If you just average from now till mid-century, we're urbanizing at somewhere between 1 and 2 million people a week, which means we're adding a New York metropolitan area of about 15 million people every few months, a country the size of Denmark every month, and a city the size of Marrakesh in less than a week. And that's pretty extraordinary and pretty amazing. And of course, that is a reflection of this really tremendous rate at which the population has grown on the planet. And I'm sure many of you are familiar with this. This is the population of the planet over the last 12,000 years, beginning from when we emerged from being hunter-gatherers. We developed language, we learned agriculture, we then formed a sedentary life, forming communities, and that led to cities. And as you can see, and as everybody's very familiar with, we had this very slow growth for the first more than 11,000 years. And then at the end of the 18th century, we shot straight up. And that, of course, was stimulated by the Industrial Revolution, the discovery of fossil fuels, their exploitation, coupled with the development of capitalism, entrepreneurship, open markets. And that's led to this extraordinary growth and to the extraordinary standards and quality of life many of us are privileged to participate in. But this is pretty amazing. If I just look at my own life, I was born around here. I hope you can see the cursor. Born around 1940, and here we are up here, almost approaching 8 billion people. So we've gone from just about 2 billion people to 8 billion people in my short lifetime. Now, I want to introduce the concept of singularity in a moment, but I want to relate this first to this population growth to every other metric that you could measure about the planet. Everything from, you can't expect to read all these, but just to give you an impression, on the left are socioeconomic metrics like population itself, GDP, energy use, water use, and so on. And on the right are what's called Earth system metrics, things like CO2, even things like fish capture and ocean acidification and so forth. And all of these have the same character, this hockey stick, extraordinary, faster than exponential growth. So we live in a faster than exponential expanding socioeconomic universe. I mean, most people are familiar with the idea that we live in a physically exponentially expanding universe, but in fact, on the planet, we're going even faster than that, or have been going faster than that, at a faster than exponential rate. And I just want to pause for a moment and give you a quote from the great John von Neumann. I'm sure many of you are familiar with the name, but if not, he's the man, maybe certainly the greatest mathematical physicist of the 20th century. He is responsible for the architecture of computers that we're using now to communicate, for computation itself. He developed game theory underlying much of economics and social sciences and the foundations of quantum mechanics. And in 1953, he made this extraordinary comment: the ever-accelerating progress of technology gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs, as we know them, could not continue. A sort of statement that you could imagine someone saying today, less so, whatever this is, 70-odd years ago. And what is sort of interesting about this statement, apart from the power of it, is that von Neumann sort of mathematized everything. He was this great mathematician. And this statement sort of came out of the blue, and he never really elaborated on it or developed mathematical theories or models to really explain what he meant by this. So in a very modest way, I'm going to try to put some flesh on the sort of the skeleton of this statement. So this does represent what I consider the mother of all tipping points, if it's true what he says. And I want to just elaborate a little bit on it by talking a teeny bit about tipping points and singularities and phase transitions to those not so familiar. We're all familiar in our daily lives with them because typically the word phase transition or singularity is associated with the change of state of material things. So the classic one being water freezing to ice or water boiling to water. The same stuff, but having a very different manifestation. And here's an example of that in terms of a graph. This is the specific heat of propane. Now, the specific heat, for those who are not familiar, is just the amount of heat needed to raise the temperature of whatever the substance is by 1 degree, raise 1 kilogram by 1 degree. And here it is for propane as a liquid. And you can see that there's, as you increase the temperature along this axis, gradually you need more and more heat. And then gradually you need an enormous amount and it goes straight up. And that's called a singularity. And that's called a phase transition, because if you continue heating, the liquid turns to gas and the system sort of relaxes and becomes more metastable. And that, of course, this picture here that I had a moment ago looks just like this. So the question is, are we approaching a tipping point, a singularity? Are we going to do something like this? And what does that mean? So that's what I'm going to lead up to, and I'm going to give a lot of background stuff leading up to that and leave open the speculations of what that might mean. Okay, so from the pictures I showed before and the data I showed before, it's clear that the fate of our planet is intimately related to the fate of our cities, and that has led me, anyway, to think about developing a kind of science of cities, or even whether that's conceptually possible, but to think about it. So I want to talk a little bit about cities first, because that's where all the people live and all the action takes place. So when you think of city, again, this is sort of the immediate image you have, the buildings, the roads, the general infrastructure, and so on and so forth. But in fact, that is just but a stage. That's like a theater. That's a backdrop for doing this. This is what a city really is. It's in order to facilitate social interaction, to create social networks, to enhance ideas, entrepreneurship, in order to create wealth, to create new things. And I found this nice picture of Marrakesh. This is what's going on here. It's going on in every city. And what you see here is what is really the essence of what's going on, of what a great city is. It provides venues, places like this, for people to come together to interact, informal public places, formal places like lecture theaters that you're in now, universities, offices, provide stadiums, and so on and so forth, coffee bars, and so on, for people to come together in order to interact. And what you see going on here is that A is talking to B, B talks to C talks back to A, and they build on each other, and they create ideas. They're continually creating ideas. We continue to create ideas. Almost all are irrelevant and pointless and of no interest to anybody else. But what is extraordinary about this dynamic is that every once in a while, this dynamic, the spirit of this dynamic, produces the theory of relativity, or quantum mechanics, or a Google, or a Microsoft, or an Amazon, or a Toyota. That's what a city does. It is, in fact, this extraordinary machine we've developed for facilitating the creation of wealth, knowledge, innovation, ideas, in order to increase the standards of quality of life of all the citizens. But unintentionally, inevitably, it creates entropy, the most fundamental law of science. The one that pervades the entire universe is the second law of thermodynamics, which says if you do things like this, if you create things, then inevitably, if you create order, you inevitably create disorder, and that's called entropy. So inevitably, that dynamic that I just described, in addition to creating all the wonderful things that we participate in, including being able to communicate with you across 10,000 miles, we also create this. Inevitably, not necessarily exactly this, but things like this are inevitable. And the challenge is to mitigate these problems, not just mitigate them, to minimize them, but problems like this are inevitable. So all of these you're familiar with, and including the effect on the environment. And what we don't want is the planet to look entirely like this, or for this to happen. So that's the challenge. And the question is, can we develop a serious science? And I'm a physicist, as was said at the beginning. I'm a physicist, and science to me means quantitative, based on principles, potentially mathematizable, but certainly computational, and so on. Computable in some sense and predictable. So the question is, how much of that can you do with this extraordinary, complicated and complex system? So traditionally, the way we deal with these problems, of course, is we put boxes around the various things that contribute to the system. Now, this is some arbitrary kind of laundry list that I just made up. We put boxes around these things and consider them almost autonomous. But of course, we go much further than this. We put boxes around the things within boxes, and within those we put boxes, and we more and more deconstruct. And overall, that has been enormously successful because it's led mostly to the kind of world we live in today, the kinds of understanding that we have across the multiple sciences and the humanities. And it has led to the wonderful products that we have, from cars and to iPhones and computers and so on and so forth. But one of the things that this, of course, neglects is that all of these things are inevitably interconnected and interrelated. Each one of them, not only that, is evolving and adapting, and each one is indeed a complex adaptive system. And the entirety is a complex adaptive system of complex adaptive systems. So this is a daunting problem to address. So given that sort of framework, we of course shouldn't have been surprised that a random mutation of a virus in China would have led to no football in Spain, the bankruptcy of Hertz here in the United States, the shortage of flour in the UK, social unrest in France, and much, much, much more with which you are very familiar. We've been through this, we're still going through it. And what is extraordinary is that all these things which seem completely disconnected suddenly became interconnected, connected to this event that happened just a few months before all these things happened. The timescale was extraordinary. Things happened very quickly. And the fact of the matter is, all these things which appeared disconnected are in fact connected, even if extremely weakly. And so this is sort of a classic example almost of a chaotic phenomenon where some small perturbation somewhere produces an exponentially enhanced effect elsewhere, encompassing a much broader span of issues than the one that stimulated it. So this is kind of amazing. So football in Spain is connected to flour in the United Kingdom, amazingly. It was, and it still is. And we have to be aware of that. So this is the mother of all butterfly effects. I'm sure many of you are familiar with it. The idea that the flapping of the wings of a butterfly off the coast of Brazil creates a hurricane in Florida. So we also have this problem. This is a silly cartoon, but this is the kind of issue that you also run into if you don't think more systemically. That is, we have this classic problem, and then we solve it by widening, having a new lane, and indeed we get back to the same problem. So we have this whole problem of unintended consequences if we don't think more systemically and recognize the interrelationship of things. So cities are a wonderful example of that, and they are, in fact, a quintessential example of a complex adaptive system. And in general, at the biggest kind of picture, a complex adaptive system is the interface, integration, and tension between, on the one hand, its physicality, its energy, resource, its infrastructure, its metabolism on the one hand, and on the other hand, the information being exchanged by the various agents of which it's composed, in this the case of cities, people, and so forth. And that's what was represented in those pictures. But the one important aspect of this is that the energy and information flow through networks, and networks play a crucial role. Here's typical networks related to infrastructure, to cities, and down on the left you see the highway system of the United States, which is, here I've shown it a bigger picture, and you can see it's sort of a jumbled mess. Of course, it's evolved in terms of response to needs of cities and response to the geography and geology of the country and so on. And it looks like sort of it doesn't seem to have much systematic behavior, but in fact, if you look through a different lens and you choose one place, here I've chosen arbitrarily Laredo, Texas, which is a port, and you ask, what about the traffic leaving Laredo and going across the United States, feeding, if you like, the United States in 1 year? And if you put that all together and you add all that up, this is what that looks like. And the thickness of those lines represents the density of flow of traffic. And what you see now is something much more regular. You see something that's fractal-like, it's self-similar, it sort of repeats itself and has a sort of regular behavior. And so underneath what is something that is relatively irregular, you see something that's much more regular. And that's the kind of thing we want to start addressing as I move into this. So networks, if you go back to this picture, of course, it looks very much like a biological network, a typical network. And biology is, of course, replete with networks. And in the middle there at the top, you see yourself. That's your circulatory system. And in fact, it doesn't look so different from this. And in fact, it isn't so different. The major difference is that the road network is two-dimensional, and this is, we are three-dimensional, but otherwise pretty much the same. But here's a bunch of networks across biology, from the microscopic all the way up to something macroscopic. And here's what's amazing, and I'm not going to go into any details on this. The physics and mathematics of these networks has extraordinarily powerful implications, and it leads to this, that is something that is extremely regular in something that's maybe the most complex phenomenon in the universe, namely metabolism. This is metabolic rate on the vertical axis versus size, body mass on the horizontal axis. And the mathematics and physics of these networks would predict that instead of these points lying sort of not exactly randomly all over the graph, as you might have naively expected, believing in natural selection, namely that each one of these organisms, each cell type, each genome inside it, each organ has its own unique history, evolutionary history. So the points would lie sort of spread around the graph, reflecting that evolutionary history, the historical contingency. No, they line up on a straight line when plotted logarithmically, going up by factors of 10 on both axes. And this represents, for those familiar, what's called mathematically a power law. But the important thing here to recognize is that there's an extreme simplicity that underlies the extraordinary complexity of metabolism if we look at it through the lens of scaling. Furthermore, the slope of this line is predicted to be 3/4, which is very close to the best fit to that line, which is sublinear, meaning it's less than 1, which means there's an economy of scale, because it means that this would be linear. It means that as you get bigger, per cell or per gram of tissue, you need less energy. So that a bigger animal needs less energy to support its cells than a small animal. And that's those are the so that would be linear, and that's what the theory predicts, and that's what it's. And this has been known. I said predicts, but this this has been known for 80 years. Basically, it was called Kleiber's law. And biology, if you take this kind of theory, you can predict 50 more such scaling laws for everything else, and I could show you many more of these. But what is remarkable about them is they have a kind of universality. They all have this kind of sublinear character, and most importantly, the slopes of them, like this graph, are simple multiples of 3/4, And here's a mundane example, heart rates versus size, and you can see it decreases with a slope of -1/4. So little animals have hearts that beat very fast, and big animals have hearts that beat very slowly, but they do it in a systematic, predictable fashion. Now, I could show you, as I say, 50 more of such scaling laws. It gets boring after a very short while, and I'm going to show you just one other. It's the -1/4, and that's for lifespan. And you can see there's a lot of variance in this, and I don't want to discuss that. And I just want to concentrate on the middle one, mammals, and the slope of that is very close to 1/4, which is predictable from this theory, the network theory. But here's the point I want to emphasize, is if you go back to heart rate, that is decreasing with a slope of 1/4, and this is increasing with a slope of 1/4. And if you multiply them together, the two 1/4s, so to speak, cancel out. The decrease of one is exactly canceled by the increase of the other if you multiply them together. And then you ask yourself, what is lifespan times heart rate? That is the number of heartbeats in a lifetime. And that should be the same for everybody. So this says that the number of heartbeats in a lifetime is the same for all mammals in particular, and there's the data, and it's kind of extraordinary. So that even though a mouse lives to 1 to 2 years and a whale lives for 125 years, if you look through the lens, if you rescale through the lens of heartbeats, they live the same length of time. And so it's kind of interesting to speculate whether they experience life the same length. So I'm going to do one other thing in biology before moving on to cities and then to the planet. And let's talk about growth. You've all done it. You've all scaled. You've all grown. And this is how you did it. You ate. You metabolized the energy. You sent that energy through the networks. At the cellular level, that energy is used to maintain cells. That is, it repairs damage that's occurred, and it replaces ones that have died and then grows new ones. And you can put that into mathematics. And the network sort of is this arrow. That's the thing that sends the energy to the cells. And you put that into mathematics and you can solve the equations. And this is what you get. This is for you as a rat. This is a rat. This is its growth curve. This is its weight versus age. And that line is a prediction of the theory, and those dots are data points. And the fact that you stop growing is directly related to the sublinear economy of scale of metabolic rate. And that leads to bounded growth. The fact that you grow quickly and then stop is guaranteed by the sublinear nature of the scaling, which is related to the control of the networks that are distributing energy. And this stability, this cessation of growth, so-called sigmoidal growth, underlies to some extent the sustainability of the biosphere, the fact that we all reach a kind of metastable state after early growth leads to the fact that we have sustainability of the biosphere and that life has been around for 2 to 3 billion years. Now, so that's great. And of course, if you try to take this over to socioeconomic systems, this would be considered a disaster. The use of a metaphor of biology for socioeconomic systems, some ways is quite good, but in other ways is very bad. And this is one of them that's very bad, because we developed this from post-capitalism, the development of capitalism. We developed the idea that we need to be sustained by open-ended growth. And this obviously isn't true here. So we want to go into that. This growth curve permeates everything. You can fit the fits aren't quite so good, but you can see. And here's one thing I'd like to just finish up with before moving into cities, and that is if you rescale these growth curves according to the theory, and you plot them versus these strange variables that I have here. I don't have time to explain them, but if you rescale, everybody grows in the same way. So again, if you look through the right lens, we all are born, live, grow, and die in the same way, roughly speaking. And here it is, including tumors. Tumors, of course, are you, and here they are. And these colored points are tumors. The gray points are the points on the previous graph, and they fit on it too. So it's a kind of universal theory of growth. So here's a quick summary of what I've said about biology, which I'm now going to take to talk about cities and then the planet. We have these systematic, universal scaling laws dominated by this 1/4 power. The number 4 is the dominant number, the number that dominates the biosphere. It controls everything about the biosphere in a kind of coarse-grained way. It expresses an economy of scale, so the bigger you are, the less you need per cell or per gram of tissue. I didn't emphasize this, but the pace of life systematically slows down. That was the heart rate slowing down. Life gets extended, you live longer. And growth is sigmoidal, meaning that you grow quickly and then stop, and then you die. And that's all explained by the dynamics, mathematics, and physics of the biological networks. So the obvious question is, are cities, I'm not going to talk about companies, but are cities scale versions of each other? Do they manifest a similar kind of universality? Well, they are networks, as I've already discussed. And so the question is, are there similarly hidden laws of biology? And not surprisingly, you can apply the same kind of mathematics and physics and network theory to urban networks. And you can derive this kind of scaling. And this is for infrastructure, this is the infrastructure. And this is, again, a mundane example. This is the number of petrol stations versus population plotted logarithmically again. And what you see is very good evidence of scaling. And what you also see is that it's sublinear. That dotted line is linear, meaning that there's an economy of scale. So the bigger you are, the less gas stations, less petrol stations are needed per capita. So this is for just 4 European countries, but we've looked at data across the globe, the rest of Europe, of course, but the Americas, North America, Latin America, China, Japan, Asia in general, and petrol stations scale like this everywhere. The only difference with biology is that the slope here is roughly 0.85 instead of 0.75. So there's kind of a 15% saving with each doubling of size rather than a 25%, but it's the same idea. What is more remarkable is it's not just that petrol stations are the same all over the globe with this scaling, but that all infrastructure is like this. The length of all the roads, the length of the electrical lines, the gas lines, the water lines, the buildings, and so on. All the various infrastructure of the city scales like this with the same slope of 0.85. That's and that's pretty amazing. And that has sort of interesting consequences. The fact that the infrastructure, you have less infrastructure is needed per capita, the bigger you are, means the less entropy is being created. And here's an example. This is carbon emissions in the United States. And I'm sorry, it's a busy, slightly technical graph, but what you see is here's the slopes. They're less than 1. So the bigger the city, the less carbon emissions per capita. Therefore, in the United States, New York is the greenest city in terms of carbon. And where I live, Santa Fe, which is a small city, is one of the worst. It's counterintuitively. So we talked about the infrastructure so far. And as I sort of intimated at the beginning, that's sort of the less interesting part of the city, really, even though it's the part we normally focus on and think about. The really interesting part of the city is what cities are actually for, is to create and facilitate social networks and social interaction. And I'm sure many of you are familiar with this kind of topological graph of social interactions. The nodes are people and the lines are connections to their friends. And this is typical graphs you see in the literature on social networks. But when you think of cities, this is missing something extremely important and fundamental, which is almost never taken into account in social network theory. And that is, well, this one part is, and this is a sort of cartoon version of it, that you have modularity. That often is taken into account. That is, you have families and divisions and groups and so on, which have a sort of regular structure. But what is not taken into account is the fact that you have to be standing or sitting or lying on a two-dimensional surface. You are tied to place. You have to be in your kitchen. You have to be in your bathroom. You have to be in your office, etc., etc. So despite this picture, you have to be somewhere. Not only that, you have to be moving. You have to go to the office. You have to take the kids to school. You have to go buy food at the store. So this is very misleading, and this means that the idea of a city, which is these pictures I've shown before, that thing in the middle is the interface between the social and infrastructural networks, the physicality and the information part. And this is what I said earlier. This is the very dynamic that is producing all the wonderful things that we participate in, and as well as the bad things. So what I mentioned earlier in terms of A talking to B, talking to C, and they build on each other, is of course positive feedback. You build on each other, and maybe not surprisingly, that leads, instead of sublinear scaling, the bigger you are, the less per capita, it leads to superlinear scaling. The bigger you are, the more per capita, and instead of the slowing of the pace of life, the increasing of the pace of life. And here's the data to support it. This is just a panel of half a dozen metrics from different metrics in different parts of the world. I could show you, of course, again, 25 or 30 of these. But they're very different things. Everything you see from good things like wages, patents as a measure of the innovation of a city. Here's restaurants, but here's bad things like crime and so forth. So all these things, and you can see just by eye, they all have pretty much the same slope, and their slope is superlinear. It's more than one, it's about 1.15, and the slopes are pretty much universal. That is, they're universal in terms of different metrics and in terms of where you measure them across the globe. And this is what it says in English. My French is good enough to translate it, but to say it in French. On average, if you double the size of a city in an urban system, or you look at a city that's twice the size of another in an urban system, then roughly speaking, you save, as I've already said, about 15% on all infrastructure, and at the same time, you increase all the good things: income, wealth, ideas, patents, education, creativity, connectivity, and so on. All those good things are increased, but also all the bad things like crime and disease and so forth, and indeed, including COVID, all by about 15%. And that seems to be true, roughly speaking, across the globe. So here's an example. A city of 10 million people will have doubled the number of COVID cases in half the time a city of 100,000 would, even though it's only, quotes, 100 times larger, and it'll have 200 times as many cases. So much better during the pandemic to be in a small town than a big city. But when you're not in a pandemic, if you want job opportunity, excitement, a sexy life, lots of action, lots of culture, much better to be in a bigger city, and the bigger the city, the better. And so, as a test of that theory, the idea is that this is derived from this positive feedback in social dynamics and social networks. This is part of a collaboration with my friends at MIT. And what we did is we analyzed billions and billions of telephone calls, mobile phone calls. They had this enormous set of data of billions of phone calls, various places, and we analyzed them to measure the connectivity between people as a function of city size. And here it is. This is for two countries. This is Portugal and the United Kingdom. And what you see is, as so to speak, predicted, the slope is the same as it is for the scaling of the metrics. This is the underlying mechanism for that. And one of the surprising things that came out of this, actually, was to ask about the clustering of people. That is, even though in a bigger city you have many more interactions, many more interactions. If you ask how big is the group of your friends, so how many of your connections are connected with each other, how many of your friends are friends of each other, you find that doesn't change. So here it is on the top, this top one is Portugal, and below here is the United Kingdom. And what you see is that even a small town, this is a town of 10,000 people, this is Lisbon, which is well over 1 million, and you have the same clustering. So it's as if even though you live in a big city with more interactions, your group of friends is roughly speaking the same as it would be if you lived in a small town or village. The only other point to make about this is you can see that the clustering is much bigger for Portugal than it is in the United Kingdom, because I'm sure many of you know people in England don't talk to one another. So one of the questions that you might wonder or ponder about is that doing what we're doing now, at least I'm doing now, is this soulless, two-dimensional way that we are evolving to interact via Zoom and many other mechanisms. And the question is, what is that going to do? Because it is removing us for a little bit, maybe a lot, from this tying of information exchange being tied to place. So that's open to question and open to speculation. I'm not going to dwell on it here because I want to move ahead with talking about the planet. I just wanted to show you some data on pace of life. On the left, I showed you that before, the pace of biological life decreasing, heart rates decreasing, and on the right is the speed of walking in cities versus size. This is both European and American cities, and you can see it's increasing. Pace of life increases. The social network has its effect, even, of course, on the pace of life. So, leading up to, can we extend this framework, this kind of network scaling framework, to understand a little bit about the time development, the growth of the planet in this way? And here I invented this whimsical term, master Anthropocene equation, and a grand theory, unified theory of sustainability. This is what we want if we're to address the questions. And I'm going to scratch the surface and give you some ideas about trying to address this, because without an integrated systemic theory, I don't think we can actually address the major problems that we face on the planet, all of which you are very familiar with. So I want to go back briefly to discuss biological metabolic rate that we started out with. So I didn't make it very explicit, but this is the rate at which you use energy, food, basically, in order to stay alive. This graph that I plotted is actually is really for basal metabolic rate. This is just the energy you need to stay alive. That's called basal metabolic rate. But of course, you also need energy to be active, and that's called either field or active metabolic rate. And what that does is that increases the metabolic rate by a factor of 2 or 3. So here it is. So it adds that it scales in the same way, but it goes up from, where are we? Here you are, man and woman goes up here. And if you look at this, if you look where we are, you may have already seen this. If you look across here, you see something extraordinary, that just to stay alive, you need less than 100 watts. That's all you need, 100 watts. That's 2,000 food calories a day. All the food you eat a day to stay alive, do stuff, is about 100 watts, which means you are a light bulb. So you are extraordinarily efficient, whereas if you ask, and this is how we were, of course, this is how we evolved, this is our natural metabolic rate. But now that we've urbanized, now that we discovered language and discovered agriculture and discovered cities and all the rest of the stuff, and created iPhones and roads and cars and refrigerators and houses and all the rest of the junk that is us, that is really us, then we have something called social metabolic rate, which is, of course, just by analogy with the biological metabolic rate, is two parts. A part that is maintenance, just keeps the whole system going, keeps everybody alive, and keeps the infrastructure maintained, and then adds new stuff. There's an active part that creates new stuff, creates institutions, creates ideas, creates roads, creates new stuff. What that does for our metabolic rate, our real active metabolic rate, is up there. Instead of being a couple of 100 watts, it's over 10,000 watts. It's about 11,000 watts if you live in the United States. So it's up by a factor of 100. And all of that is been evolved since we stopped being hunter-gatherers. That's pretty extraordinary. And you can ask yourself, if you go back to this graph, how big an animal is each one of us, roughly? Here we correspond, our 90 watts corresponds to where we should be, some less than 100 kilograms. Now we can ask, what is this? This is about 30,000 kilograms, 30 tons, each one of us, in the United States at least, and where each of you in that room are not so different. And there are getting on to 8 billion people on this planet, all of whom want to have social metabolic rates that approximate this 30,000 kilograms. This is extraordinary, and it's an amazing achievement, frankly, but it also has dire consequences. Oh, yes, also, you're equivalent to about a dozen elephants. So, by analogy with the growth equations I've already talked about, biological and cities, we have the same thing, except it's driven by social metabolic rate. It's the same equation, same idea, and that's going to be the equation. This is what led to, originally in biology, to the cessation of growth and the sustainability of the planet. Now what we have is with superlinear scaling, driven by that social metabolic rate, we get open-ended growth. And that's good. That's actually very good, because it says we have a lovely theory, a lovely self-contained theory that is highly consistent. That is, we have this idea that at the basic level, we have social interactions. They have positive feedback. That positive feedback leads to superlinear scaling, and superlinear scaling leads to open-ended growth, which is what we see. So the theory is highly predictable in that sense, and this is just a cartoon version of what the theory predicts, and you can understand the growth of cities in that way, and including the dips and bumps that occur. You see that one for London, and also this graph for the entire planet is all encompassed in that. And so that's great. But this theory that can explain this, both qualitatively and quantitatively, also leads to something called a finite time singularity. And that's finite time singularity in the equation is technically is illustrated by that dotted line. And all it means in English is that that curve growing faster than exponential is going to become infinite at some finite time. That is, it may be meaning that in some finite time in the future, it might be 5 years, 10 years, 50 years, 100 years, but at some time in the future, this thing is become infinite, which is nuts, which is crazy. You can't have infinite GDP, you can't have infinite number of AIDS cases, and indeed, the theory tells you what happens. It tells you that if you go beyond that singularity, just as we saw with those graphs of propane, it's a different, it looks different in terms of the mathematical form of the curve, but the system stabilizes, collapses, and that's bad, of course, that's terrible. So it's a kind of, in a way, if you like, a fancy neo-Malthusian argument that you can't have open-ended growth, eventually you're going to collapse. So how do you get out of this? How do you stop this? Well, let's just go through an exercise. What you realize is this graph, I'm just going to do it symbolically here, this graph was derived assuming that the parameters for all those things in the equation remain pretty much the same. And of course, in a certain sense, they do, because we have a certain paradigm. You have something called the Stone Age, the Iron Age, the Bronze Age. You have the Industrial Revolution. There's a paradigm that completely sets the background, the cultural background, the physical background to the way society develops, to the way people behave, to the way we produce things, and so on. And so with that in mind, and of course the modern one being the invention of computers, followed by another major change, the discovery of the internet, and so on, and the exploitation of the internet. So this gives you a hint as to how you get out of this collapse, and that is that as you grow within this paradigm, within this major innovation, somewhere before you hit the singularity, you better make a major shift, you better make another major innovation or paradigm shift and start all over again. And of course, you would hit another singularity, and you have to make another major paradigm shift or innovation and start over again, and so on and so forth. So you have a kind of theorem that if you demand unbounded growth, open-ended growth, then you require continuous cycles of innovation or paradigm shifts to avoid collapse. Well, people have talked about that for a long time, but the new thing here is that you have to do it faster and faster in a predictable way. And you have to have these accelerating cycles of innovation in order not to collapse. So that's what the theory says. And I may get sued for this. I don't know. I stole this from the web. This is what you see here, those numbers, those things there are maybe not innovations. They're certainly inventions, but this could be thought of as a smaller scale version of what I'm talking about. And that is those numbers in parentheses, in brackets, are the time to reach 10 million customers. So it's a kind of proxy for the increasing rate of innovation. And indeed, if you take these numbers and you plot them, they agree precisely with this theory that I've just described here, the rate at which those events have to take place and so on, and the time differences between them. And I've stole this from a man named Kurzweil, who has been promoting the idea of singularity, but his idea is completely different about singularities. His is, of course, that we're going to have this kind of, it's almost as if the Messiah had come or whatever, but some wonderful world of cyberspace. But he concocted this graph, this picture, and what it is, just let me explain very quickly. This axis here is how long time ago something happened. So life evolved over 3 billion years ago. That's when it began, so to speak. And it took over a billion, 10 to the 9th is a billion, over a billion years actually for that process to happen, to begin. And then it just comes down through life. I'm not sure I believe all this. But then, of course, as we get to social things, it just, on this scale, it just goes straight down. So that you end up with computers that happened maybe 20, 30 years ago in terms of at least personal computers. And it took just 20, 30 years to develop. So it's all on the same graph, and you can plot it logarithmically. But what is interesting, the theory predicts this line, predicts this blue line here. And if you plot it logarithmically, that white line is predicted by the theory. It's just plotting that same graph logarithmically so you get everything on it. So going back, let me just go back, sorry to do this, to this. The theory predicts the form of that curve, and it predicts how the system approaches the singularity. And this is what it says. it says if you plot logarithmically a major socioeconomic metric of the globe, such as I say, energy or water, for example, versus the time to get to the next singularity, TC is called the singularity here, TC minus T. So more technically speaking, if you plot log Y, meaning Y just being one of these major metrics, versus log of TC minus T, the time, whoops, that's my timer to tell me I should stop. This should yield a straight line with a predicted slope. So it predicts the slope, the theory, and it predicts that it should be a straight line. And here's data on energy. And I want to warn you here, hold it first, let me find the cursor. This is log of TC minus T, which means time that we're in goes backwards. We're approaching the thing, so time goes this way. So this is 2008, and this is 1975. And you can see it agrees with the prediction. I haven't got the slope on there, but it agrees with the prediction of the slope remarkably well. And that's great. But what, to our surprise, when we started looking at this and looking at the data, it also predicts this, that before 1975, in fact, from about 1950 to 1975, it was also a beautiful straight line, but it has a different slope. And looking at, I can't go into the details, but this is the prediction, and this is the data. This is it. So if you didn't know any of the theory and you simply plotted it this way, this is what you would get. So this is kind of amazing, the regularity of this, the prediction of it, and the prediction that we are approaching a singularity, and that in the mid-70s, we actually avoided a singularity by making a change, and that leads to all kinds of speculation. But here I just want to show you first the same thing for water and many other metrics, which I'm not going to show you. And that leads to this speculation. What happened in the mid-70s? I don't know the answer to that. There was the oil crisis, but probably most importantly, that is the origin of that rate, is the combination of the oil crisis, which was a major hit, but the globalization, the beginning of globalization, a radical change in the way commerce was done and the economics of the globe were being started to change at that time. And I think this represents that. And so this tells you, if you can do the good statistics on it, when the next singularity will be. This is also for the markets. I'm not going to go into that. And I'm going to finish up here because I'm going to leave open questions here for speculation. I should say one thing about this. It's the fitting to this and doing the statistics leaves open the time to the next singularity. It could be anywhere from 20 to 40 years. In terms of the statistics, it favors something more like 25 to 30, but it's somewhere in that range that we're going to go. If we don't, something major doesn't happen, we're going to go over the edge of the cliff. And major means something maybe like the invention of the internet. It could be, of course, something as mundane as self-driving cars. Who knows? But we don't know. That's open, as I say, to speculation. So just to finish off, this unbounded growth leads to this finite time singularity, which means that you have to innovate faster and faster. And this is an example of the accelerating pace of all socioeconomic life. Life is, I'm over 80 years old, and I can tell you that life is significantly faster now than it was when I was a young man. And most importantly is this last point, I think, is that socioeconomic life has got faster and faster, but we've got the same brain, basically, and the same biology we've always had. Namely, it's the same brain and biology that we had when we were hunter-gatherers 10,000 years ago, or even 100,000 years ago. And yet we have to adapt to to all the extraordinary changes that are taking place. I was just forced, just as an example, I had an iPhone 6 that no longer worked. I had to buy an iPhone 14, which has all kinds of bells and whistles, where that's a trivial kind of adaptation. But there's adaptations in terms of adapting to overleaf and Slack and this and that, and then they invent something else and blah, blah, blah. And yet we're the same. And I believe that this is causing great social economic anxiety, which leads to many of our socio-political problems. So we're basically like Sisyphus. We push the boulder, we're destined to push the boulder up the hill, and then it rolls down again, and then we have to push it back up. But Sisyphus had it much easier than us, because in Sisyphus's case, he pushed the boulder up and it rolled down at the same rate each time. But for us, we have to push the boulder up faster and faster each time because it rolls down faster and faster. So we need a new paradigm. I believe we do need some kind of big conceptual systemic framework based on complexity science, something that's integrated, holistic, mechanistic. It has to be computational. It has to be predictive. And of course, coupled with the extraordinary advances in big data, machine learning, and AI. But the warning, I'm very concerned about the mindless use of big data and AI, but I think we'll overcome all that. And hopefully we can get out of this and solve the big problems. So I don't have time. I've gone over my time. Just it's been an extraordinary collaboration, a bunch of young people who have now got major careers, but these are the biologists. And the point I want to make here is that they have very different backgrounds. Some of them are traditional biologists and ecologists, but some are computer scientists, physicists, chemists, and so on. Down here on the left hand, here's Alex, who came in as a physicist, turned into a biologist, and is now a professor of psychiatry. And here's the ones for the social stuff. My major collaborator here was Louise, runs the big institute at the University of Chicago, two young students, postdocs, she's now a professor at the Sloan Business School at MIT. She's a professor at Northwestern Business School. He's an anthropologist, et cetera, et cetera. And these are all the senior people on it who did no work. These are all the people that did no work. And I will finish there, and I apologize for going too long. Oh, I should add these. These are the one on this latest work on the Anthropocene, also part of the previous collaborations, actually. Anyway, I'll finish there, and I apologize. These are the people that supported me, and I thank you for listening.
Thank you. Thank you so much, Dr. West. This was a wonderful talk. And, demographic transition and the growth of human population in the past couple of centuries is really one of the most historical development that we've, one of the most important historical development that we've lived. And you've likened this to the growth of organisms. And we know that the timing of growth in organisms is governed by hormonal and epigenetic mechanisms. And I was wondering if there were equivalent mechanisms when it comes to the timing of urban extensions, right? So the timing of growth spurts in urban expansions.
Yes, are there? Well, that's like asking a question, a related question, a metaphor that's often used, like using genomics, or the idea, is there a DNA of a city or a DNA of a company? Or in fact, a kind of DNA of the globe, but it's a collective. So it goes very much, by the way, I should have said that during the talk. This is really all to do with collective dynamics, obviously, because it's integrating over, social networks and over societies and cities and so forth. I don't know the answer to that. I've actually not given a lot of thought, to tell you the truth, to whether one can use these terms like, the hormonal content or the genomics or the DNA more than just metaphors. They're fine as metaphors, but I'm not sure that it's possible to identify them. Maybe it is, and maybe ultimately we need to do that and make them so to speak, more concrete and something like that needs to be integrated into the theoretical structure.
Thank you so much. I would like now to invite Dr. Stuart KAUFFMAN, who is going to be giving a commentary on the talk we've just heard. And so, Dr. KAUFFMAN is a medical doctor, but he's also an emeritus professor of biochemistry at the University of Pennsylvania, a seminal member of the Santa Fe Institute, a MacArthur Fellow, and a Trotter Prize winner. And I hope you all enjoyed his talk on Wednesday. And today, he's going to be commenting on the talk we just heard. So,
hi, Sarah. Where's the little red thing here?
Yeah, so this is...
Geoffrey, we miss your voice here. Geoffrey WEST and I are very old friends from the Santa Fe Institute. That was a spectacular talk, old friend, and there's a great deal to talk about. So I'm going to try to talk about several things, namely in response to you. Oh, I can look and see what I said here. Geoffrey WEST is presenting us overwhelming data that we really are approaching a singularity. The issues are, in fact, global in scale, civilizational in scale, and they're existential in scale. I've told you about TAP when I talked the other day. Geoffrey, I think you've not yet heard this. I managed to get my slides to you, I think, 2 hours before you talked. TAP is the theory of the adjacent possible. Let me offer, could you leave that, please? Let me offer it to you, Jeff, to think about as a candidate for the underlying mechanism. It does two things. As I'll show you, I showed everybody else, it reaches a finite time singularity in an increasing number and complexity of things over time. And Andrew Little proved a wonderful theorem. Every time you add a new item, the waiting time for the next new item is cut in half. It is that is driving the increasing pace of technological evolution. So the same framework is going to explain two major features that WEST has talked about. Jeff, I think it's worth considering that this TAP process that generates an increasing number of items and niches for the items in which they can make a living, be they organisms or goods, itself invites the increasing use of energy. But it need not. And I'll get to that in a minute. So let me just remind you of TAP. That's the equation. I'm not going to interpret it for you other than to say MT plus 1 is the number of things in economy at time t plus 1. MT is the number of things in economy at time t. And all the stuff on the right says, how many new things can I make out of one? Suppose that MT is 20. How many things can I make out of any single one of them? How many things can I make out of any pair of them, like the printing press? How many things can I make out of any 3 of them, or any 4 of them? The Wright brothers airplane is a recombination between airfoils, light gas engines, propeller, and bicycle wheels. Brian Arthur, also of the Santa Fe, has pointed out economic growth is by recombination. This has now become a large body of work with the people that you see above, and an overlapping group of us is now publishing a paper in Cambridge University Press explaining technology as the growth of this process. So this is your graph also, Jeff, seen in another way. This is per capita GDP for the last 2,000 years. It's flat, and it explodes around 1850. Yes, the Industrial Revolution. Notice, as Geoffrey said, per capita GDP is exploding vertically, 14-fold. It's wonderful. It's lifted millions of people from poverty. It's extended lifetimes. It's increased education. But it can't keep going vertically. We're on a finite planet. This also is a singularity, and it's driven by TAP, as I'll show you next. So this is the TAP equation put into an economic form. And it has the property that if you started with a modestly small number of things, for a very long time, it increases very slowly, that it increases super exponentially, it's more than hyperbolic, and it reaches infinity in a finite time. That's us, on the right. We're heading for a singularity. I'm not going to show the other things it does, except to say again with Andrew Little, every time you add a new item, the waiting time for the next new item is cut in half. Or it might be cut by less than a half. That's going to require more deals to work. And that gives us the increasing pace of technological change. My case is my father was born in 1902, or 1903, the year the Wright brothers invented the airplane. 66 years later, my son was born, the year we landed on the moon with a different technology. 10,000 years ago, not much happened in 66 years. Technological acceleration is real, we're living it, and I'm the same as Jeff is, and I promise you life is faster now. And I don't care about much of the new doodles that come out every month on yet another thing. Okay, so TAP actually implies two ways to collapse. One is going beyond the singularity. Geoffrey, this is what you told us about. There's another way embodied in this TAP process. As I've written it, things never disappear. But if you put in it a tunable first-order loss term, mu, you just say for any given thing, there's a chance of 1 in 10,000 that it just disappears, or 1 in a million, or 1 in 100, or 1 in 10. So mu is a tunable term, death rate. Fix mu, well, let mu increase from 0. So there's no loss, then a little loss, and a lot more loss. There's a transition. Below that transition, this process goes to infinity in finite time. Above it, it collapses to 0 in finite time. So this is a different collapse. There's no warning that you're getting near this collapse that we can find in the data. And we have the following problem. If we wish to slow economic growth, for example, by raising interest rates, that would increase death rate. Therefore, the whole economy might collapse, and we wouldn't know it until it collapsed. It's a very major issue. I want to turn now to some of the stuff that Ivar Elkland told us. He's right. We're going to need complex, multi-pronged responses to all of the mess that we're making. But I want to raise an issue that's terribly important. I grew up in the United States, and we had Smokey the Bear. We were to not start forest fires, and we didn't. And the understory overgrew, and we get forest fires now in the United States. They're hideous forest fires. We knew we were doing the right things. We made a mess of it. How will we know, as we rush now to save the planet, that we're doing the right thing? By what metrics will we know, particularly if it's multi-pronged? I trained as a doctor. When you change a patient's medication, you don't change 17 at a time, you change 1 at a time. We're going to have to do multi-pronged. We may be making bad mistakes, and worse at the bottom, since things are happening faster and faster and faster, how will we handle things when the pace of change is getting faster and faster? We have no idea. Okay, I want now to talk to next steps. Geoffrey, what you talked about is a wonderful link to some hopes. I am talking to us here, to the president of the university, and I hope to others in power here in Morocco, and for others, about global creative commons. The basic, I think we need to do this now. This is not a joke. We need to create platforms that span globally with computational platforms. For example, for farmers in Morocco, farmers in the United States, farmers around the world, to gather local data on their farms and try little experiments. Do I change this? Do I change that? Do I change the soil? Do I change the microbiome? Do I change whatever? So people all over the globe, picture millions of farmers all over the globe having access to reports on their local conditions, trying little experiments to try things better or worse, and sharing it with the colleagues they want. We are trying to create something we will call a distributed peer learning network. I think we can stand it up in the next 3 or 4 years and coordinate soil work and agriculture using this all over the globe. But the same thing will work in medicine. I'm just talking to the president of the university about that, and colleagues of mine and I are trying to do it. But we can probably do it in many domains. There's something magic about it. My colleagues and I showed some years ago that if you have groups of people who share information, but on the basis of merely anecdotal evidence, not statistically significant evidence, almost just hunches, and they keep trying with one another, they can solve very hard problems, combinatorial optimization problems, better than otherwise. We begin to understand that we may be able to learn how to learn together in a distributed global way. We've never done it globally. This also ties into something you said, Geoffrey. We gather in cities, in part because of the social interactions at high cost, but meanwhile, our friend groups are about the same size that you just showed us. I begin to wonder if we have distributed networks of these kinds, can we maintain social gatherings of the size that we can handle as humans? Somehow we will have to deal with the fact that it's very good to be together in person. Another thing about cities, people run into the cities because the wages in cities are higher typically than rural wages, so people go into the cities to make money. If we do global commons and we distribute the capacity to invent, for example, out to local farmers or anyone, they will make the money because they're the ones doing the invention. That may decelerate urbanization. Okay. I want to end with this. I was just in a conference in Australia. A wonderful man named Roland Fletcher, who I'm going to introduce Sarah to, is an anthropologist who studies essentially civilizational evolution. Roland stunned me. He says the next, and this relates to what you were saying, Geoffrey, he says, I think the next great transition is going to be beyond machines. I think machines are going to become a thing of the past and somehow vanish in the next 200 years. And he says every transition does that, and the seeds for it should be forming now. Well, I think they are. In my own talk, I discussed beginning to understand how the evolving biosphere creates ever new possibilities by which creatures get to exist with one another. We cannot use any mathematics based on set theory to deduce the new adaptations in the biosphere. In fact, we can't use any mathematics based on set theory to deduce the next innovations that will happen in the global economy. We can't deduce them. We live them forward. So we can begin to do genetic tests and others to understand how, for example, mixed microbial communities create ever new possibilities with one another. And we can begin to understand how the evolving biosphere has exploded in diversity, but it's done it with constant energy input from the sun for 4 billion years. I want to now pause to say something I haven't quite tried to say before. TAP appears to apply to the evolution of life. As Geoffrey showed us, life started 4 billion years ago. For 2.5 billion years, you had single-cell organisms, prokaryotes and eukaryotes, then a flowering of multicelled organisms and the enormous Cambrian explosion 550 million years ago, which was hyperbolic. Since then, in what's called the Phanerozoic for the last 600 million years, good evidence shows that the increase of the number of species and above them of genera and above that of families are all hyperbolic. They're faster than exponential. Put that together with the fact that the cost is roughly constant, namely the number of heartbeats per life hasn't gone up. The biosphere is a vast network that's an economic network as well. Creatures exchange, my garbage is your food. If I'm a bacterium, my flat surface is the highway on which you can walk to get food. We haven't the faintest idea how billions of creatures make their livings with one another, and they've done it with a constant energy input of the sun for 4 billion years. The biosphere knows how to do it. If you go out in the woods, there's not a single machine. It's really interesting, not one. So somehow the innovation that I think we're looking for may not be what we think at all. It may be to learn how to, the biosphere has done it for 4 billion years, and we must maybe learn how to learn from and participate in the unending, unprestatable, non-derivable creativity of the biosphere. I found myself saying, Homo at last sapiens. I think I mean it. There's something vast that is almost growing, and I have the sense that a lot of it can happen here in Morocco and in Africa. This continent is not yet despoiled by our unending greed and the stupidity with which we keep creating things that we just don't need. Somehow we have to do it. There may be pathways. Thank you.
So thank you so much to Dr. KAUFFMAN for his commentary. I just wanted to say briefly that, well, actually, you're right. I think Morocco and the African continent is really well positioned to tackle this kind of issues. And I'd like to tell you actually about the work that members of our school, the School of Collective Intelligence, including our scientific director, Dr. KAUFFMAN again, and Dr. James Winter, Dr. Ed Seabright, and myself are involved in collaboration with local farmers here in Morocco and with the organization Al-Mutmir. So we aim to create a public access repository of agricultural information and traditional knowledge with the long-term goal of sustainability and farmer empowerment. And so we are in the early stages, but yeah, I hope you'll keep an eye open as we progress. And now we're going to take a little break, a little 5 to 10 minute break before we carry on with our next speakers. So yeah, thank you so much, and thank you so much to both Dr. West and Dr. KAUFFMAN for this wonderful morning.
Ladies and gentlemen, friends, the discussion in the lobbies are almost always the most interesting discussions, but I suggest that we start again. Sarah, if you can control your crowd. You know, do you see the next orator? Okay. Floor is yours. So.
All right. So welcome back to our session on complex problems and collective solutions, hosted by the School of Collective Intelligence. So first up with us will be Dr. Virginia CHAITIN. Dr. Virginia CHAITIN is an epistemologist and a philosopher of science, and she's going to be talking today about the benefits of interdisciplinarity and about methodology for conducting interdisciplinary research. So please help me welcome Dr. Virginia CHAITIN.
Okay, so good morning. It is obviously a great pleasure and honor to be here talking to you today. After this whole week at this wonderful venue, I feel I am with friends, talking to friends. And yes, I am bringing today an epistemological analysis of interdisciplinary research because what I feel, listening to all the talks, is that interdisciplinarity is basically present in complexity theories, because there are many theories of complexity, there are many concepts of complexity, and they bridge many disciplines. However, as an epistemologist, as a person who worries about the methodology with which science is practiced, I have realized over the years that many times multi- and interdisciplinary research are not conscious, epistemically speaking. People exchange ideas with practitioners of other disciplines. They use concepts from other disciplines, but not always is there an epistemic analysis of what is actually going on. So this is the contribution I hope I will bring to you. I would start asking what and how does interdisciplinarity happen in practice? How can we carry it out, being sure that we are having some epistemic gain? Why isn't it better for us to just continue doing our research in our own departments with our fellow colleagues and not have the problem of having to relate to a different culture, to a different intellectual history, to a different vocabulary, to a different conceptual framework, and sometimes even to different forms of reasoning. So how can I carry it out? Making sure that I am advancing in conceptual gain. Methodologically speaking, interdisciplinarity is very complex. I think everybody realizes that, in the sense that it deals with unexpected and many times difficult encounters and even impossibility of exchange and understanding of what is coming from this other area of study that I am not specialized in. So for this, I propose a pluralistic epistemology in the sense that it views knowledge in general as a combination of permeable conceptual frameworks instead of a history where each discipline is developed in an independent way. This combination of permeable conceptual frameworks also exchanges rationality rules, epistemic games, methods, and techniques, and above all, languages. When we look at knowledge from this perspective, we're going to identify many appropriations of conceptual frameworks or conceptual networks, if you will. And sometimes these appropriations are made non-isomorphically. That is when problems begin. If you have a complete isomorphism between, let's say, math and physics, it works beautifully. Or even between math and economics, which is a little more difficult in the sense that many economic concepts might not fit precisely into the mathematical representation. But when you are putting together, like we do in complexity theories, in the area of complexity, things that range from sociology, anthropology, biology, physics, mathematics, the whole environmental realm, then we are dealing with non-isomorphic conceptual migrations because many concepts are not 100% mathematizable, for example, and many mathematical concepts cannot be really understood by the sociologist. Oh, thank you. And to make things even more interesting, the epistemic goals, meaning, for example, I want to understand this, so I need an equation for it. That's an epistemic goal. Understanding in anthropology does not necessarily require an equation. So this is what I mean by an epistemic goal and different epistemic goals. Different methods for attaining an epistemic goal and different techniques. But this is, despite of sounding a little hopeless, the fertility of interdisciplinarity. Interdisciplinary studies, you all know, I don't have to preach to the converted. I realize that here there is this intention. There is this disposition for working interdisciplinarily, but still, it never hurts to try to be really conscious of what is going on at the epistemic level. So the fertility of interdisciplinary work is really given when you realize that there are problems that you could not solve, that you could not even state them without using vocabulary that comes from a different area that is not your own, and suddenly you can find a very good and accommodating formulation for the problem. I remember at high school, I had a teacher who said, the solution for a problem starts with a good formulation. I never forgot that, and I realized that interdisciplinary research gives you the possibility of making better formulations for problems and therefore finding better solutions. This is why interdisciplinary work should lead to better, what we call, it's an epistemic goal in science, explanatory power. Putting together these different vocabularies, conceptual frameworks, forms of thinking, manners of reasoning, and even styles of reasoning is non-trivial, and we can't really improvise. It does require specific education. So it is wonderful that here at UM6P, we are not waiting for graduate studies to present to the students an interdisciplinary view of knowledge. because it's not easy to improvise, as I said. Once you're already in the marketplace and you suddenly are faced with a complex problem, you are going to work with people from different areas that are not your own, and you suddenly don't know how to bridge the gaps. It requires, therefore, a special education, a specific education, and also a specific psychological and emotional disposition. Yes, our thinking is influenced by our emotions. So we have to be open for this exchange and for change within the exchange. If we look at a practitioner or at a body of knowledge that comes from an interdisciplinary effort with suspicious eyes, because why is it that this person is using mathematical language? Or why is it that that person used a certain metaphor? We are not opening our cognitive abilities to understanding what the person meant. And I like to cite Gorgias in The Sophist. He gave us an advice. How do you say? It's a wise man is the man who believes in everything he reads, but only as he is reading it. What does this mean? You have to read it with an open heart. Okay, so I noticed that here we are today in this School of Collective Intelligence, and also that there is a new chair at the UM6P that is named Complexity and the Humanities. So this is why I feel that here you are taking interdisciplinarity as something serious, something positive, and there is really a commitment to this understanding. This is how I see it. Needless to say, complexity itself is already interdisciplinarity, and mixing it in with sociology, anthropology, the arts, philosophy, you name it, you are really beginning to establish a profound dialogue. And I would think that imagining a methodology for this dialogue might be fruitful. I like to consider an analogy when you are getting in touch with someone from a different academic background, and now you have to work with this person. You have to perform academically with this person. It is nearly like you are learning a new language. So interdisciplinary research and learning a new language are very analogous. It is not only about learning new words, new meanings, understanding the different syntactic structure for the sentences, but it's also about learning really a new form of thinking. There is a different music, a different tempo, if you compare different languages. There's a different form of perceiving and apprehending the world by different languages because they're inserted in their culture, and there is a disciplinary culture in academy. So you are learning, you're broadening the way you look at the world every time you learn a new language and every time you actually embrace interdisciplinary work. It is a new système du monde that you learn how to enjoy, I would say. I would like to bring a distinction between multi and interdisciplinarity, just to provoke your thoughts when you are working with people from different areas. We all know what multi and inter means. When you think about it epistemically as applied to working with people from different areas, a multidisciplinary research will involve people from different areas, but it will not necessarily have the same entangled state between the conceptual frameworks, the methods, and the language that you do have when you go really interdisciplinary. Sometimes it's not necessary, we don't have to do it, but if you do feel that you have to create a new vocabulary, a new conceptual system to tackle the problem, or the problems, or the phenomenon, then interdisciplinary comes. You have the emergence of a new conceptual toolkit when you work interdisciplinarily. And I think it's interesting when you are conscious that this is happening, even when you are going to explain your research to someone, even when you're looking for funding. Funding agencies are important in our daily lives, and if we explain to them that what we are doing is actually novel, I think that it's usually helpful. Telling them this is not math or only applied math to something. This is actually a new field that we are creating. So I guess I already mentioned the non-isomorphic concept migrations. This is exactly what I'm referring to as the emergence of a new vocabulary. And I would say that an interdisciplinary education is about acquiring the special proficiency in this kind of thinking. So what I notice is that students and professionals that actually embrace interdisciplinarity, they become more flexible in their thinking, and they become broader. This can happen without you being aware of these epistemic details that I am naming now, but I think that it's fruitful, it's useful to realize that this is what is going on in interdisciplinarity. It takes an effort, but it pays off, and I would say that intellectual mobility is at the heart of interdisciplinarity as much as it is in the study of complex systems. And to finish, I would like to congratulate really UM6P 6. I think it's an important thing to say. Someone has to actually say, we all know it, but I would like to congratulate. The kind of education that you are providing for engineers that will not merely be aware of the social impact that their work has. Being aware is already something, but it's much more than being aware. I feel that here, with this collective, integrated intelligence, the engineers graduating from UM6P will be understanding the problems they address, the solutions they are proposing, tailoring these solutions to the desired social impacts. So it's not that, oh, we have the solution, let's see how this impacts on society. It's the other way around. And this is of great importance for Morocco, for Africa, and since, as Geoffrey and everybody else here this week mentioned, we are all a whole global complex system, so whatever you're doing here will definitely impact the entire world. So thank you very much.
Thank you so much for a wonderful talk. I mean, of course, when we are facing global challenges that require we innovate very quickly, I think we cannot do without interdisciplinarity, and this is something we have to learn how to do very more efficiently and increasingly in the future. And so, so thank you very much, Dr. CHAITIN, for your intervention. And so our next speaker is Dr. David NAPIER. He's a professor of medical anthropology at University College London. I'm very happy that there's a fellow anthropologist as part of this session. And so his work combines research and public engagement to tackle important problems, including access to primary healthcare, homelessness, and human trafficking, with a particular focus on vulnerable groups such as migrant and ethnic minorities. And so today he's going to be talking about why it matters to measure complexity in health research. And I'll pass it to...
Morning, everyone. Thank you very much, Sarah, for the kind introduction. My name is David Napier. I direct the Science, Medicine, and Society Network at University College London. Today, this talk is about complexity in health and specifically about our efforts to develop data on complex relationships, often complex relationships that are hidden, especially amongst vulnerable populations, and that resist data analysis, but that do have serious health impacts. The example that I'm going to use is the rising challenge of non-communicable diseases and of diabetes and obesity, and particularly in cities, where the rise in these health challenges is really not only quite dramatic, but also very difficult to address at the level of policy, and also principally because it demonstrates the kind of complex big data analysis in health that Geoffrey WEST and Stuart KAUFFMAN are calling for. So let me just jump right into this, and I'll try to make this as succinct as possible. I'm not going to reiterate the complexity of cities. I think we got a terrific introduction to that already, but just to point out that clearly part of the challenge is the immense flux that we're faced with, and especially in new and emerging megacities where you have terrific and unexpected and oftentimes unpredictable transformation. So in 2014, we started a public-private partnership between these groups, UCL on the right there, funded and sponsored by Novo Nordisk in Denmark. This was called Cities Changing Diabetes, and we're now in 40 some cities globally, representing, working with public health departments representing populations of more than 250 million people. So why are we doing this, and what do diabetes and obesity have to do with complexity? Go through this very quickly, but worldwide there are now an estimated 537 million adults currently living with diabetes. And to put this in perspective, if it were a country, it would be the third largest country in the world. So the challenge here is really quite extraordinary. It's especially complicated at the level of data when you look at something that we use in non-communicable disease research called the rule of halves. So the rule of halves is a pretty simple idea, and it's not accurate for any specific country, but it is accurate globally and gives you a sense of why we must urgently address these challenges. What it says is that for all the people living with diabetes, that's the column on the left, only about half of those globally are diagnosed, only about half of those are actually receiving care, about half of those achieve their treatment targets, and about that final half, that very small line at the end, of a single row of people achieve their desired outcomes. So this is not a good profile when you're a policymaker thinking about how to invest your healthcare funds and where they're actually going to go. But this graph tells us something actually very interesting, because if you look at what's happening, that top half, the people who are undiagnosed, I mean, we may say they're living with an illness, but they're just living. It's not diagnosed for them. So it's not actually a risk factor that they're aware of or thinking about, but it's this middle domain, that gray domain, where we're looking at issues around what we classically call adherence and the ability or inability to adhere. And it's only that final bottom row, the orange row, where it doesn't matter if you're wealthy or poor or integrated or not. You have access to resources, you don't, because this is the only group that's achieving their desired outcomes regardless of what's going on socially and culturally, and that's the point that I want to make. It's not very big, is it? not very big, a big set of people a large set of people who actually, for whom diabetes is only a medical issue. Remember that, because if we then look at its largest risk factor, which is obesity, which are now on the left-hand column here, and we realize that the 2 billion, a third of roughly of the world's population that's currently obese or overweight, the rule of halves falls pretty dramatically. This is the most important risk factor now. That rule of halves drops pretty dramatically. That third largest country in the world is now a pretty small column, and indeed the achieving desired outcomes, I mean, we put a gray line there, but it's actually a thread thin line drawn across a real desert of ignorance. So really, when you think about what we're actually able to know about this disease, if we think about it only in medical terms, we're facing a dramatic challenge. So what do? Well, what we did was, of course, what everybody does. We looked at the evidence, and we started to look at various places where you find evidence, and we were pretty startled by what we found. Web of Knowledge, only about a little over 8% of all the publications on diabetes have anything to do with the social sciences or humanities. To refer to the previous talk about interdisciplinarity, when you look on Scopus, it's less than 3%, okay? So that's less than 3%. That means that more than 97% of all the publications on diabetes are for that thin line, only the thin line. So the question is, how do we get at this, and why therefore is the kind of complexity research we're talking about really critical to the future of world health? Because remember, in most countries, diabetes uses about 20% of any healthcare system's expenses, diabetes mortality, morbidity. Well, there's that pile of knowledge, and the question is, what we realize right away is that the problem is that diabetes and obesity resist normal kinds of research that we do, and this is the WHO Health and All Policies framework, and you can see that the problem is we're looking at the need for data, health and housing and water and sanitation and transportation and health communication. Now, I'm not going to read the list, but you get the point that there's a lot of heterogeneous data out there, and the question is, how do we look at it together, and how do we understand how these risk factors compound one another? So that's one thing. The other thing is the knowledge that health is largely created outside of the health sector. So the health sector doesn't have this data. 8,766 hours in a year, right? About 6 hours a year, and if you're lucky in the UK, that you're going to be spending with a doctor. Okay, that means that's what you're spending your time. That's where you're spending your time. And what that means is that data doesn't translate. And of course, what this leads is what I heard about yesterday about unknown unknowns, Donald Rumsfeld and so forth. And this is the recent, 2018 now, so it's a recent Lancet review on health inclusion, and you can read that for yourself about the absolute absence of data in this area. It is precisely what we would call these health and all policy domains. And of course, what this is I know this is kind of a cliche using the iceberg metaphor, but I think it works really quite effectively here. So what do? Well, with all these cities that we're working with, we introduce access strategies for accessing those unknown populations. I won't go into the details of this, but we don't only look at service utilization. We also look at social capital in the middle domain. Then we do something that other people don't. To get to the comment about anthropology previously, so we actually go out and do field work, because the thing you realize immediately is that for all these people who are not able to manage, they're in a state of calamity coping, where the thing that may be killing them is may not even be on their list, and they're not the people who are going to show up for any of the usual places where we would expect to find data on them. Randomized controlled trials eliminate variables; they don't compound them. Surveys, you have to have time to fill them out, and focus groups. Well, who has time for that if you're in a state of not even being able to manage your disease? So you have to actually go out and find people, and to understand it. So that's what we ended up doing. And of course, what we realized, and again, this is not AI. This is just very simple common knowledge. But we realized that you could extend this beyond biological, social, geographical, cultural. You could add many other risk risk factor columns. But the idea here is just to understand that what's actually happening in that area of non-adherence is you can draw your lines anywhere across here to come up with what we call a case definition. You can go up and down columns and connect them. But the point is you have to know what the dominant risk factors are for any particular group, and you have to understand how to analyze those, how to create these case definitions of vulnerability in which these risk factors are compounding one another. It does no good to do to separate them out and to look at the effects of smoking on cancer. It's not going to tell you what's happening in these non-communicable diseases. So what we've done is we've come up with a visualization of this. We call it the vulnerability vortex, and you can see it roughly imitates the vulnerability assessment strategy, formal networks, community networks, and then we have what we call the vulnerability threshold, and that's the point where people kind of fall into the vortex and disappear. These are people who've lost their health advocacy, who can't actually represent themselves, and who we actually have to go out and study in order to know what actually the triggers are and what the tipping points are that move them in and out of being able to become advocates for their own health destiny. And that's why on the one side we have at the top people fully capable and those at the bottom not, and why we have at the top fully socially integrated and those at the bottom not. And in fact, we should probably, where we have basic survival needs, it's sort of an inversion of Maslow's hierarchy need, at the basic bottom line, that should probably just be a darkened area because that's the, as it were, the black hole of health research. Now we know this because in our work with disease changing diabetes, we now have thousands and thousands of hours of interviews. Now we're able to look at various drivers of the illness, and if you look here on this, you'll see, I don't know where the mic is, but anyway, you can see here on the top, these are basically proxies for health equity, and you can see we thought this would be a lot higher because we talk so much about equality of health for everyone that when we asked people the extent to which these had an impact on their inability to manage their diabetes, we got roughly 35% of people. When we asked people about proxies for health inclusion and invisibility in health agency, lack of family support, lack of friends, so on and so forth, that rises to 93%, almost everybody, almost everyone. So the need to understand inclusion is really quite critical here, and I won't bore you with the details, but I'm happy to say that the UNICEF and here the Lancet, the systematic neglect of culture and healthcare is the single biggest barrier to the advancement of the highest standard of health worldwide, okay? The Lancet, Robert Wood Johnson Foundation there on the left, WHO Europe, that these emergency alarms are going off, people realizing that the importance of understanding complexity in health data is really absolutely critical for actually addressing the problems that face us, especially in densely populated urban areas. And indeed, I'm happy to announce, I'll finish with this, that as of last year, UCL, we began working with The Economist on a health inclusivity index, and this is an effort to understand, as we say here, the process of removing the personal, social, and cultural, political barriers that prevent individuals and communities from experiencing good physical and mental health, and I say this most importantly, at the level of health humanities and big data, a life fully realized. In the first year, we just launched this in November. You can see these are some of the countries that were looked at. This is not a judgment of a country, but the idea here is to shift the discussion from health equity and equality, as important as they are, to understanding what happens when people are not included and how exclusion itself is actually driven. And indeed, in the first year here, you can see that we have 20% on the right-hand side. I won't go through this whole slide, but 20% of countries in just this first year have policies, explicit policies, that exclude members of their own, certain members of their own populations from healthcare. So, I invite you, you can go to the Economist Impact Unit and you can look on their website. This is the dashboard. I don't have time to run a live version of it, but the idea is that you can go into the dashboard and you can manipulate certain factors, certain indicators to try to see in what way you can take action on health inclusion and what potentially in any particular setting might advance that. This is a fairly rough go at this the first year. It will be refined over the next several years, but meanwhile, thank you very much for your time.
So thank you so much to Dr. Napier for a great talk. I have many thoughts and questions, but I'll keep them for the roundtable for the interest of time. And now I would like to welcome Dr. James Winters, who is an assistant professor here at UM6P at the School of Collective Intelligence. Dr. Winters is a cognitive scientist who works on the domains of collective intelligence, technology, and communication. And today he's going to be presenting his model of open-ended technological evolution and problem solving.
Hi everyone. Is this how we control the slides? Yeah, this? Yeah, okay, great. So thank you everyone for having me here. Today, I'm going to talk, I've sort of got a shorter title, which is Optimization Traps and Open-Endedness. Problem discovery has a hard constraint on technological evolution. I just sort of want to preface this as this is joint work with Mathieu Charbonneau, who's also an assistant professor at the university here. And basically, this was my pandemic project. I only had access to a computer and my code and some math. So I put that to good use, I think. And this is what I want to present to you today. And I want to kick things off by saying that humans have used technology and culture to adapt to nearly every environment on Earth. And this is a really curious feature of human behavior that really sets us apart when we compare ourselves to other non-human species around the globe. So if you take one environment, such as the Arctic here, you'll find species that have developed biological adaptations to these environments, such as polar bears, and they've adapted to have things like extra layers of blubber, large pores, and specialized carnassials. But by contrast, humans have been able to survive and thrive in these environments through technological solutions, through creating parkas, mucklucks, and harpoons. And when we look at the sort of success of human cultural and technological adaptations, it more or less exhibits this cumulative growth dynamic that is underpinned by sort of three general properties, which I call the basic recipe of cumulative adaptation. The first is we're able to generate novel solutions, either through incremental or combinatorial means. We can then take these solutions and in the context of an environment or a social problem, we can filter them to discover effective outcomes. And then finally, and perhaps in some ways most importantly, we're able to transmit knowledge of these solutions and technologies socially within a group, but also across generations. And when we look at this topic, more or less this notion of cumulative adaptation is used to explain a variety of dynamics, is used to explain how our technologies become optimized to environments. It's also used to explain how we've seen an explosion in the growth of diversity of our technologies and cultures. And then finally, it's also used to explain how we've developed increasingly complex, modular, combinatorial solutions. And what I sort of want to highlight here, which is sort of jumping off the back of what you saw earlier with Geoffrey WEST, but also on Wednesday with Stuart KAUFFMAN, is that as a species-wide capacity, the evolution of technology is an open-ended process, so it keeps growing. And importantly, as we've seen in various graphs shown throughout this week, this rate of cumulative growth accelerates as we approach the present. And the big question is how did we go from a species located in Africa 60,000 years ago that suddenly spread out, colonized every corner of the globe, more or less, that went from these basic stone tools like Acheulean hand axes to, as I said just now, modular combinatorial components. And if you're wondering what that is, that's an example of a modern gaming mouse. And there's a variety of ways we can study this, and today I just want to talk to you about one approach which I'm particularly passionate about, which is computational modeling. And when you survey the literature on computational models, I think there are, there are a variety of issues. I mean, models aren't perfect, they're abstractions, but in the context of cumulative culture and this open-ended dynamic, I think there are two issues. And the first issue is that I think many of these models marginalize or ignore the role of problem solving. So what do I mean by this? Well, basically, I mean normally the emphasis in these models is on generating, transmitting, and amplifying solutions, and less attention is paid to the underlying problem that's being solved. That's just taken as a given, it's an abstraction. Sometimes it's modeled using something like a utility or payoff function, but for the most part, it's just an abstract concept and there's no sort of dimensionality to the underlying problems. The second issue I want to focus on, and I've sort of taken a quote here from one of the articles that Stuart KAUFFMAN was discussing in the context of the TAP equation, is that a lot of these models are focusing on the preconditions for accelerated growth. And what I mean by this is that this highlights a sort of necessary set of preconditions for these accelerated dynamics to emerge, but this isn't the same as saying that these are the sufficient conditions for accelerated growth. And I think one issue I have here with some of these models and the way they're presented is that it leads to this notion of an explicit or implicit conclusion of inevitability. So if we wanted to rerun the tape of history, essentially we get the same outcome, which is accelerated growth. Now, the problem with that is, of course, we get accelerated growth. We're all here right now. I'm talking to you using computer technology that's a result of rapid acceleration in technological progress. But the problem is, really, for humans, we only have an N of 1. We only have one sort of substantial observation of this historical trajectory. So I think the notion that it's an inevitability that we would end up with this complex society that we live in today is not necessarily the case, and this is something I want to push back a little bit with my model. And specifically, in the context of problem solving, I want to argue here that any model of cumulative dynamics needs to explicitly state its assumptions with two causally interacting search processes. The first of which is seeking out solutions for an existing set of problems. And on the other side, you can almost invert the causality of this process, and you have something that I call problem discovery, which is instead of seeking out solutions, you seek out novel problems to solve. And I think when you consider this problem-solving dynamic, problem discovery dynamic, it leads to some very interesting outcomes in these models of cumulative growth. And specifically in the model I'm going to show you, this will have a dynamic that has a search space over both the problems we solve and the solutions that we generate and transmit. And importantly, this allows for the underlying search space to both expand and contract, i.e. it's dynamic and open-ended. And specifically, my focus here is on two features of problem solving. And I saw this more two comments on problem solving and why I think it's important. First of which is that problems vary in complexity. It takes time, energy, and resources to solve existing problems, but also to discover novel ones. The second point I want to make is that it's not just the case that problems vary in complexity. Individuals and the groups they're a part of have agency. They can choose which problems they solve. They can use information about their environment to make decisions. And I think that's a very important feature that is often missing in a lot of these models that we've seen. So if we run with the assumption that populations are active decision makers and also they can choose which problems to explore and exploit, then I think this raises the following question. To what extent does problem discovery constrain the long-term growth dynamics of technological evolution? So to do this, I'm going to sort of give you a very brief and non-technical as possible whirlwind tour of a model I'm calling BitWorld, which primarily aims to investigate the evolution of technology, but I think it's a pretty broad and general model. And the basic gist of it is that this is a computational model of human societies using technologies to generate solutions and to solve and explore problems. And the basic setup, hence the name BitWorld, is that we use bit strings to model the idea of solutions and problems. And the basic setup looks like this. So we have a repertoire of knowledge or technologies, which are bit strings. And then we use this repertoire to generate solutions, which are also bit strings, and then we use them to solve problems, which again are also bit strings. And importantly, in this model, the societies and the individuals in these societies have no knowledge of the underlying problem. So they have no notion of how good their solution is for solving a given problem. And the way in which they gradually figure out how effective a solution is through getting feedback. And I use a basic edit distance metric to measure this. So the societies are able to gradually get feedback about how effective their solutions are for solving a problem. And this is basically the backbone of the first dynamic of the model, which is solution seeking, which is a process by which populations generate a filter for effective solutions to existing problems. And they basically have three strategies for achieving this. They can either maintain their existing set of solutions, they can incrementally modify this solution in a simple way, or they can use a combinatorial model where they can combine from their solution repertoire completely novel solutions. Then, and I think the sort of novel step of the model is in terms of problem discovery. And I'm going to talk to you a bit more about this in a minute, but to just sort of give you a brief summary, that this is a process whereby populations use and update their search preferences to seek out novel problems to explore and exploit. So this means that the problems societies are solving aren't static, and I think that's a really important point to stress here. And then finally, this model forms an inheritance dynamic where the transmission of the repertoires that a society has, as well as the current problems and the search preferences they have, are inherited from one generation to the next. So this forms the complete sort of overall system of the model. Now, to sort of talk a little bit about problems discovery, and I'm going to try and go through this quickly, problems discovery basically forms four basic features. First of which, in order to engage in the discovery of new problems, your existing solution needs to be relatively effective for solving its current problem, which is what I call viability. And this is determined probabilistically based on the effectiveness of solutions. Then a society needs to generate a set of hypotheses as to where to search for new problems. And then they engage in the actual search process, where they use a sort of a Bayesian model, essentially, to look for problems in the search space using three basic strategies. The first of which is a conservative exploration strategy, which is where a society maintains search within the same space of problems. They can have an expansionary strategy where they try and look outwards and try and look for more complex problems to solve, or they restrict their search, which I call restrictive exploration. And importantly, this sort of model dynamic allows for a feedback loop between the process of searching for novel problems as well as how the societies and the individuals within it update their preferences. And what this means is the societies can gather information about successful and unsuccessful searches, which essentially means that a society can learn from past events and use this information to guide future decisions. So, that's the sort of whirlwind tour of the model. And what I'm going to show you now are simulation runs where we assume the society has access to all the necessary preconditions for accelerated cumulative growth. We have high fidelity transmission, populations have access to rich mechanisms for generating and filtering for solutions, and the storage capacities or the storage resources of a population can grow indefinitely. So basically, we've equipped a society, we've given them every advantage in life to have accelerated growth. And then for the discovery dynamics, what I'm going to assume is that initially the search process is unbiased. So, and I've modeled various biases and preferences here. The model is quite rich and more complicated than what I'm going to show you here. But we're going to initially assume it's unbiased. And by this, I mean that a society starts out with no initial preference for the types of problems and the area of the search space it's going to explore. But as I said earlier, the society can update its search preferences in response to successful and unsuccessful searches. Oops. So what do we find? So what I'm going to show you here are two axes. On the vertical axis is the difficulty of the problems a society is solving, and on the bottom axis is time, or the number of generations. And when we run this simulation with unbiased exploration where the societies can update over time, what we find is that for the majority of runs, I'm not showing all of them here, the majority of runs end up in what I call optimization traps, which basically means that the societies, even if they exhibit some growth, they eventually end up in this absorbing state where they solve a restricted set of problems. And the basic reason why this happens is twofold. First of all, there's this notion that it's easier to find novel problems as opposed to trying to find hypothesized problems in larger search spaces. And then the second aspect is essentially that the solutions the society are generating become specialized for and over-optimized for solving the problems. You can liken this as to something like statistical overfitting, where essentially you can't generalize beyond your existing solution repertoire. Now, this is the same set of runs, but I've zoomed out to show the full range of the model up to problems difficulty 5,000, so length 5,000. And what I'm going to show you now is the rest of the runs in this simulation. So what we see here are the sort of characteristic hockey stick-like growth where we get this accelerated growth. But importantly, this occurred with exactly the same parameters as the other runs which ended up in the optimization traps. And this sort of stresses the important point of the talk, which is that accelerated growth is rare. If we rewind the tape of history, to use the metaphor applied by Stephen Jay Gould, then the dynamics only on the rare number of cases converge on accelerated growth. And it could very well be the case that what we see here today is a result of compounding rare events. We're the ones on the lucky trajectory, but if we rerun the tape of history, this might not have happened. Now, I'm sort of emphasizing this point, and I'm sort of pretty much out of time now, but I sort of want to say that what I showed you there were a bunch of runs from the same initial starting point, but we can also use these models to rerun the tape of history from various different starting points on a given trajectory. So here I'm taking a single trajectory, and I'm taking the output that it generated at different time steps, and then I'm feeding it back in, and I'm letting the model run again and again and again for hundreds of times. And what you find if you restart it at generation 500 is that you get basically the same finding in the sense that even though we've started it on a trajectory which in one run exhibited accelerated growth, for the majority of runs we end up back in optimization traps. However, we do have a slightly higher probability that we're now going to get accelerated growth. And the same also holds if we now look at it slightly later on in the time series of this growth at generation 1000, and we also again rerun the tape of history, where now we have a much higher probability of exhibiting accelerated growth. But again, we still get lots of scenarios in which it essentially goes back and the societies end up solving a restricted set of increasingly simple problems. In short, history acts as a strong constraint on the long-term dynamics. So, to summarize, or to conclude, if there's one thing I want you to take away from this talk, then it's that the inclusion of an explicit discovery process can lead to radically different dynamics, even if you start with the same initial conditions and parameter configurations. The main thing that's driving this process is history and how it feeds back with our search preferences. And if you want to take something else away from the talk, then if we assume search preferences are initially unbiased, then optimization traps are in fact the norm. Societies are content to solve a restricted set of problems and avoid the costs of expansionary exploration. And then finally, under the right set of historical circumstances, accelerated growth can emerge, and this growth becomes more probable but not inevitable as we solve increasingly complex and difficult problems. So with that said, I'd like to say thank you for listening, and I would especially like to thank Sarah Alami for chairing this session and helping organize everything.
Thank you so much, James, for your talk. I was just informed, sadly, that we may not have time for our roundtable, so I'm going to pass it on very quickly to our next speaker and do my best to make sure we have a few minutes to at least address a few questions to our speakers. So our next speaker is Dr. PEIL KAUFFMAN, who will be talking about the science of emotions.
Can everyone hear me all right? I'd love to thank Rada and everyone for this amazing opportunity. My name is Katherine PEIL KAUFFMAN, and my professional mission in life has been to understand the emotional system, from clinical and social psychology through biology, down to the underlying chemistry and physics. Some of my guiding questions have been, why do we have feelings? What is their biological function? Why do they come in two categories? Those that feel good, like joy, trust, gratitude. Those that feel bad, like fear, sadness, and hate. And mostly, why is it that emotion, both our good and bad feelings, are ground zero for some of the very best and the very worst of human behavior? So the answers that I've found change a lot of what we think we know about emotion, about life, and about ourselves, and particularly how emotion operates as a core driver of behavior on both individual and collective levels. Well, so we have limited time today. I hope you'll forgive me for offering just a series of the most relevant sound bites, beginning with the key take-homes from my own emotion work. Okay. Got a little thing here. First, as my title suggests, emotion is an ancient sensory system rooted in simple binary bodily feelings of pleasure and pain. Second, feelings deliver evaluative information, informing original forms of adaptive mind. Third, feelings automatically move and protect the body, driving the ubiquitous hedonic pattern of behavior evident across the entire kingdom of animals, toward that which is beneficial and away from that which is harmful. Fourth, feelings serve the ancient evolutionary function of self-regulation, constructing, stabilizing, integrating, and expanding all aspects of self-identity. The emotional system is nothing less than an innate behavioral guidance system that has been historically opaque to science. So understanding our emotional biology can shed light on much of our misguided behavior, both at individual and collective levels. Indeed, Stuart and many others have told us about our dire situation with the Anthropocene, emphasizing our runaway global economy as a central driver. Stu explained how we're poised for a transition in science beyond the reductionism, determinism, and mechanism of the Newtonian paradigm, much of which preempted deeper investigations into our emotional nature. Newtonian determinism cannot explain our active agency, the intelligent doing behavior of animals. They suggest the suggestion that there's some sort of information processing, even free will, and some sort of subjective experience. But to my mind, the damage was done much earlier than Newton. I would start with this guy, René Descartes, grandfather of the machine metaphor, as well as empiricism, rationalism, and much of Enlightenment thinking. Despite his brilliance, he misled us in two key ways. First, his empiricism was largely observation and description, ignoring actions in the world necessary for survival and adaptation, foraging for food, avoiding predators, building niches. But perhaps worse was the dualistic identity structure with a ghost-like mind separate from yet interacting with a machine-like body. This gave birth to a traditional rationalism that credited the mind as the higher source of reason, goodness, and even personal identity. I think, therefore I am. Demoting emotion to the lowly machine-like body, perhaps even fallen, animal instinct, and the dark, dirty Freudian subconscious. So these foundational assumptions echoed across our 20th century social sciences, and certainly in James Watson's original science, behaviorism. Living creatures became just hardwired bodies, responding directly to environmental cues as stimulus response instinct machines. By design, the mind was left out. It was an unknowable black box. There was no mention of emotion, which they soon had to smuggle back into the story due to Ivan Pavlov's discovery of associative learning, classical and operant conditioning, which undergird all learning, through the application of external punishments and rewards that tapped into an unconditioned stimulus-response pair, which was actually our hardwired approach and avoidant responses to pleasure and pain. But perhaps the most tragic misstep is known as the naturalistic fallacy, the idea from George Moore that no values can be found in nature, that you can't get an ought from an is, and specifically that to explain the good in terms of natural properties like pleasure or desire is false. Now, this is most ironic because Moore was misinterpreting the words of David Hume, who himself grounded evaluative meaning in emotion, our moral sentiments, as he called them. But he made the same mistake as Descartes by ignoring doing behavior, and the fact that one can be doing something well or bungle the job, which is instrumental ought right there. Now, so surely being alive or dead connotes value to living systems. Oops. Fortunately, did I do that right? The complexity science has paved a conceptual path forward, moving us from machines to systems, from parts to wholes, and especially from quantity to quality, where we will find the self-regulatory function of emotion rooted in the self-organizing dynamics of complex adaptive systems. So again, with your forgiveness, I'll offer the sound bites of how complexity science puts a new spin on both our puzzling and neglected features of life. So the requirements of our new story paradigm. First is a more nuanced concept of identity, because emotional information always concerns some aspect of self-identity. It's our self-regulatory information. Identity is reframed as a nested fractal structure with a special organization and functional closure that affords distributed control at both local and global levels. Second, we need a rethinking of boundaries in light of the openness of non-equilibrium systems in their local environment and the biological relativity of those environments across levels of scale in time and space. Third, factoring in self-regulated behavior as both causal and creative, whether it's computational or thermodynamic work. Fourth, the question of subjectivity in terms of feedback, cybernetic feedback signals, biosemiotic signaling, and self-making autopoiesis and inactive forms of cognition. Finally, and most importantly, values, simple rules for life, and how good and bad feelings inform us of universally right states, delivering semantic value, teleological purpose, emergent from edge of chaos criticality, which we haven't heard much about yet. So these pieces come together in a new way of thinking about identity. And Stu talked about this. It's a special structure he refers to as the Kantian whole, where the parts exist for and by means of the whole. All living systems are such Kantian wholes, like this set of Russian nesting dolls, stacked one inside the other. Each eukaryotic cell, for example, collectively forming the tissue of a specific organ, say a liver, collectively united into an organ system, say by a brain, all inside one body that's moving about, constantly interacting with its local environment. So this new flat fractal identity is much better aligned with how our biology defines the self in dynamic self-organizing systems, as well as self, not self distinctions required in genetics, epigenetics, and immune regulatory processes. There's plenty more to say here about that special kind of closure. It's variously known as constraint, organizational, and informational closure, but for our purposes of the self-regulatory discussion, there are two key pieces. First, identity itself at a network level has both dual aspects, as an autonomous me as a whole, and a we as a part of a greater whole. So it's this identity itself within each level of a Kantian whole. Second, that the bidirectional information flows are born of couplings of positive and negative feedback loops that deliver binary logic that is common across each level. So, the take-homes here from complexity about emotion is that feelings themselves serve as feedback signals concerning the self-relevant changes in either internal or external worlds that require immediate action. Feelings carry a common binary logic. Its values, ultimately rooted in what's known as the edge of chaos criticality, where computation, information processing, and sensitivity are all said to originate. So semantic values that are applied in our self-regulatory emotional nature concern a bistable balancing act between order and disorder at each level across the self-system. Feelings provide both simple rules and nearest neighbor information, providing behavioral guidance at both individual and collective levels. Dual aspects. I know this is a lot to take in, and again, for your forgiveness, let's turn back to the science of behavior as it is today. And this time, we'll look at the well-known concept of the OODA loop, which is now used to understand and guide both group and individual behavior everywhere, from business leadership to military operations. OODA is an acronym for an ongoing decision-making cycle proceeding through the 4 steps of observe, orient, decide, and act. The goal is to continually learn and adapt in ways that keep the best match between internal and external environments, the most accurate mental mapping between immediate needs and actual events and features of the real world. To proceed through the cycle quickly, one can act optimally and even gain a competitive advantage and get inside the OODA loop of an opponent. So, in the context of the old behaviorism, the first 3 steps of the OODA loop, observe, orient, and decide, are tasks of the old black box mind. Building just such an artificial mind is now the design challenge of artificial intelligence, the goal being to build a robot that can observe, orient, and decide, as well as act with some degree of general intelligence, despite an ever-changing environment. For example, a creature can spot a sudden predator, say a bear in the woods, and instantly run away. Designers build fancy sensors to observe the outside world and use big data and probability matching to decide, and actuators to act. But how to orient remains a problem, even with the best deep learning neural networks. This is also known as the frame problem. Which features of the environment to observe as relevant? And while wonderfully Cartesian, robots cannot adapt. The logic is all syntax with no semantics. As Luke Steele told us, something is clearly missing. However, nature solved all these problems long ago by embodying living systems with some simple binary semantic sensation. In one fell swoop, pleasure or pain calls attention to self-relevant environmental features and orienting observation of good or bad environmental affordances, threats, and opportunities. That's an evaluative decision. And it moves the body to act, all 4 steps. Now, I'm not claiming emotional sentience solves the hard problem of consciousness. That's a different discussion about the fundamental capacity to observe. But in this new view, notice that the mind has lost its job. We're back to just a body responding in its world. Where did the mind go? As it turns out, an inactive, autopoietic mind emerges from the emotion-driven OODA loop to the degree that there is some memory of the behavioral response, which we find even at the level of the simple bacterium. Instead, when we examine the sensory motor chemistry of the bacterium, we see an early cybernetic behavioral control loop, physically instantiated on its cell membrane, where binary feelings run the entire autopoietic show, beginning with an ongoing comparison between self and not self, between inside and outside worlds, detecting external stimulus from heat, ions, peptides, sucrose, and even single photons that signal self-relevant imbalances that trigger self-corrections. The feeling signal provides both stimulus and response, driving real-time behavior via a phosphorylation signal, then feeding back via a methylation mark, establishing evaluative memories on a longer time scale, which paved the way for associative learning. This simple circuit delivers what Dennis Bray calls infotaxis, consistently moving the critter toward and away from environmental features that are good or bad in terms of survival and adaptation. So here we have both self-reference and the origins of mind long before brains emerged on the evolutionary stage. We also have 3 out of the 4 types of autopoiesis that Luke Steele's told us about. No brains required, only membranes. And these same mechanisms on the cell membrane are still in use, undergirding cell signaling cascades within multicellular organisms. But when brains did come on the scene, the binary information component in emotion began to complexify and diversify with some of the 5 basic emotions, which are joy, sadness, fear, anger, and disgust, apparent as early as reptiles. I want to point out that 4 out of 5 of these basic emotions are painful. Some people think this might be a throwback or a defect, but actually, with this new science, it's because nature is giving us 4 times as much information about what to reduce, to avoid, to prevent in our external and internal environments. It's only with mammals that we begin to see much more of an elaboration of the one basic emotion that feels good, which is joy. But then we begin to see all kinds of beautiful things like social bonding, cooperation, play, and the emergence of complex emotions like wonder and courage and, well, That's us mostly. Anyway, this evolution of emotion is also reflected in the triune structure of the human brain. So we have all three of these levels of information, and they each tell us different things about integrating and optimizing the self. This trend is also evident in Maslow's needs hierarchy and in Erikson's stage models of psychosocial child development. Plus, we also see evidence of the dual identity, that Kantian me and we, that part and whole, all the way up. From the very beginning at the bacterial level, there's quorum sensing, using just slightly fancier peptides to know when there's enough of self in the external environment. So they can get together and cooperate in balling up against antibiotics or take a virulent launch on a competitive species. So that's a really key point here about identity and how it plays out in our emotions. So Hume had it right with moral sentiments. Darwin had it right about the role of emotion in both adaptive behavior and group selection. He talked about altruism and moral instincts for the good of the community. But so was Lamarck about the role of immediate behavior that's driven by felt needs and what we know about epigenetics now. But so was Henri Bergson with his notion of élan vital. For although discredited by the mechanists who won most of the arguments, it turns out that the emotional system itself is the physical mechanism that instantiates both the animation and guidance once attributed to an identity structure called spirit or soul. And who are we to assume knowledge of the ultimate boundaries of our fractal identity structure, our creative potentials we have yet to self-actualize? So here we have a summary of exactly what this tells us about values. What does it say about good and bad and right and wrong? Good and bad are about optimal self-regulation. They're about a balance between stability and growth. Remember, this came from positive and negative coupling of feedback dynamics, something that's been missing, which is why we're doing this amplification. There are no negative feedbacks, and yet we have them. 4 times as much information about what to reverse, trends to reverse. So pleasure and pain both push and pull us to maintain an optimal balance between chaos and order, between growth and protection. Ongoing development of mind, which means growth is really about expansion of the mind, expansion of the world that you can get about in. And mostly, as Peter Singer says, it's expansion of empathic boundaries to include more and more and more of our social other. That's the primary form of growth that's going on here, and that's what we see in complexity. So I just want to say, and wrong is failing to do any of that. But I want to note that there's no us versus them in this story, because that's ultimately a conflict between the two aspects of identity that are part of all living systems, because they're part of complex systems. And there is no good and evil in this story. That's a false dichotomy that has been used to dehumanize and divide and hijack people's OODA loops, by the way. Also, too, what we do see in this new story is a radical egalitarian justice for the rights of all living systems and a radical accountability to nature's self-regulatory imperatives and simple rules. Life is trial and error, and we have feedback in every moment to tell us. We cannot know how life will unfold, for as Kierkegaard said, we live life forward, but we understand it backward. That's why our feedback signals are so important to know how we're on track or not. We come equipped with a natural flow of ongoing self-relevant feedback information there at the ready every moment of every day, lurking in our common everyday feelings. But we have evil. We have actually inverted the logic. We have not understood what the 4 basic pains are asking us to do, and we've allowed an elaboration of complex negative emotions to take root in our minds and in our cultures, Johan talked a little bit about distorted beliefs, faulty beliefs. And mostly, if there's any evil in this story, it's backward living because we're off track. So historically, we missed the boat and on the guidance system, particularly our distress signals, which is what negative emotions are. We have missed the self-corrective message and been blaming the messenger, associating our lower emotion and animal instinct with it, or even associating with evil. In fact, several of the 7 deadly sins are emotions. We've inverted the logic at every level. We've normalized ever more complex. Like I said, we have the distress signals. We've normalized ever more complex negative emotions like anxiety, shame, resentment, contempt, envy, hate. These are distress signals of an underdeveloped and misguided mind. And we've actually increased the conditions immeasurably. There's a whole sphere of man-made distress, which is a lot of why a lot is going wrong here with epidemic depression and all of that. So that's pretty negative. But there is hope, because Western science ignored value, doing, and emotion. The great religious traditions have not. So, although they missed out on motion too, and there's a lot of mistaken stuff there, the common strand across all spiritual traditions comes back to a collection of complex positive emotions: love, gratitude, respect, egalitarian, unity. We have that wonderful transcendent experience where we feel greater than the self. Our emotions, simple little joy, has pulled us toward self-development. That's what this is really about. In fact, Darwin was right, because pleasure and pain are a subjective reflection of the criteria for natural selection. Positive emotion is about optimal adaptation and growth. And it's when you look at the underlying force in self-organizing systems where you see this increased complexity, that's what we're supposed to be doing. That's the right kind of growth. It's not about more stuff. It's not about a GBT where we're making stuff and we're consuming way more food than we need because we're driven by so much negative emotion. It's about right states of being and becoming. You see all through the traditions, these common strands that lead back to the one power of complex positive emotion. Now, there's one thing I do want to say. If there is a golden rule, there's a new one that I call the emerald rule of morality. It is, do not do unto others that which causes you pain. Because pleasure is very malleable and personal, and there's lots of flexibility and freedom, but pain is universal. There's 4 very clear things our negative emotions basically tell us to do. And if we're not doing those things, we're going to have a whole lot of trouble. So, I'm sorry, I'm probably running over here, but don't get me going. So, who's that guy? As Stuart suggests, we are at a third transition in science. The emerging of a new paradigm suggests we're really of nature, not above nature. We are, in fact, active, integral participant, co-creators, endowed not only with legitimate degree of free will, whatever that may be, but the guidance to use it optimally. The co-evolving biosphere, econosphere, and our noosphere across vast scales in space and time truly are the co-evolution of nested Kantian wholes, bigger and bigger and bigger collections of self and how we understand our very identity. These from soil to our collective soul. These are the self-actualizing fruits of our universal preference to pursue ever more complex emotional rewards. So armed with this new understanding of integrated identity, organizational dynamism, self-regulatory imperatives, and simple rules, we can now begin to consider creating global structures, laws, and capacities that evoke, invite, and enable global citizenship. Thank you.
Thank you so much to Dr. Katherine KAUFFMAN for your talk. And so unfortunately, we were scheduled to have a roundtable, but we ran out of time. I was hoping for it to be a lively discussion on how our institutions might be lagging behind this exponential growth in ideas and technologies and what we can do about that. But I'll just say thank you to all of you for coming to this session. Thank you so much to all the participants. And I believe that now I have to pass the floor to my colleague, Fouad Laroui, who's going to be closing the Week of Science. So thank you so much, and yeah, I hope to see you next year.
Thank you, Sarah. Dear friends, colleagues, students, my name is Fouad Laroui. I'm the initiator of Science Week. What a week! What a week! But as I said at the beginning, les meilleures choses ont une fin, the best thing come to an end. So this is indeed, thank you, Sarah, this is indeed the closing address of this third edition of UM6P Science Week. Don't worry, it's going to be short, and we can go and have lunch. I'll start by thanking all the brilliant thinkers and scientists who have accepted our invitation. By the way, I would like to ask Reda Ben-Kirain and Saad Tazi to join me here, because it's a collective effort. I would like you to be here, guys, with me. So I'll start by thanking all the brilliant thinkers and scientists who have accepted our invitation. For some of them, it was the first trip to Morocco, no, to Africa, in fact. I hope it did not deceive. Then I wish to thank the CEO and chairman of OCP, Dr. Mustafa Tarab, for his constant and very generous support of our Science Week. There's someone who actually believes in what we do. I want to thank the young and dynamic president of UM6P. He's my boss, Hisham Al-Habti, for his unwavering support of our effort. My friends and colleagues, Saad Tazi and Reda Ben-Kirain, have done a superb job in organizing with me Science Week. Without them, this edition of Science Week would simply not have taken place. So I'll give you, Reda and Saad, a couple of minutes, couple of seconds, to say a couple of things, and then I will resume my closing arguments like we are in open court.
Hello, everyone. I'm at the end of this fantastic Science Week. I would like to remind that UM6P's ambition is to be a world-class university. So what is like to be a world-class university? Well, it's to tackle such an ambitious topic, complexity, and to be able to organize what already is a premiere, probably the most important complex summit and complexity that has ever been done. So you can, I want you to realize what the scope and the breadth of, and the exceptional high caliber scientists that we've been able to gather all together. There is a shared spirit, and we have now organized a summit on complexity. It will be prolonged on a website, so all these sessions, very dense, needs to be listened again and viewed again and again, with some very rich material, but we ambition to prolong this Science Week by a book, which will be a sum on complexity. So hopefully there will be we will pursue this path together. I think, as I mentioned in the beginning, that we must work together, and working make the path. And well, it's a beginning, and I thank you, all of you, for your efforts. All the university personnel was fantastic. I want really to thank them for this mobilization. Thank you very much, and ila liqa, inshallah.
Well, there's nothing much to add. We're really happy to have you here. We're really happy to make science happen. And I would like to thank all of you. And I would also like to thank all the teams that have made this possible. I cannot name everybody, but
I will thank them too, you know.
I'm talking in the name of the team. And it's really a good event that happened here. And it took a lot of efforts. Sleepless nights, and I would like to thank Salima, Khawla, Widad, Amin, and Yasmin, and everybody who worked behind the scenes to make this happen. And we really look forward to pursuing this dialogue through the book that Reda mentioned, but also we have a set of conferences during the whole year, and if you want to be part of this cycle of conferences, I'd be happy to share some information with you and to host you again. Thank you again.
Thank you, Saad. Yes, I was not going to forget to try not to forget nobody. Well, the project manager of Science Week, Yasmin Maouni, she must be there somewhere. She started with a beautiful gaffe. After her appointment as project manager of Science Week, I sent her a WhatsApp message. Yasmin, let's meet on Monday. It was a Sunday. Yasmin, let's meet tomorrow Monday to talk of Science Week. To which she promptly answered, Fouad, I have no time to meet on Monday. I'll see you on Tuesday, 4 p.m. Well, I had to explain to Yasmin that there is a difference between the Pope and the Cardinal. Me, the Pope, you, the Cardinal. And after that, she did a great job. The back office, as Saad said, Amin Barrada, Min al-Ahbabi, Salima Tikra, Hawla Hafidi, Widad al-Hamdawi, with a perpetual smile, Lamia Idbihi, Yassin Luqid, Nur al-Huda, Majda, the whole staff of Avant-Scène with Miriam, and Saeed Adi. Well, I'm sure I've forgotten someone. Please blame it on Yasmin al-Maouni if I forgot someone. And by this, I want to close this address. And Saad Tazi has thought about a wonderful way of really closing Science Week by a concert of Gnawa music, which will be held this evening 7 o'clock. For those who know Gnawa music, I know you will be there because everybody loves it. For those who do not know Gnawa music, you have to be under the pergola at 7 o'clock. Or here, it's going to be here, yes, because he has a contingency plan. Saad Tazi told me a couple of weeks ago, we have to have a contingency plan in the case that it will rain on Friday. I told him, it never rains in Bangui, so we don't need a contingency plan. He was right. Thank you very much, and see you next week.
There's a short 5 minutes recap of this crazy week.